Yes.
Yes, sir.
Okay. So the last question, anybody attempt that question? So you have an identical nodes, or you can of binary, you have to tell how many different binary you can create it, which have a different structure or shape. So you have to basically find out fn, where n is basically a number of identical nodes. So we have given some example when if n equal to 1, so it's just one binary tree. So answer is 1. If it's 2, so it is possible that's root and that could be left tree, and it's like a right. So answer is 2. If it is 3, it's like this is one possible way you could arrange 3 nodes, or it's like this, or other it's like this, the similar image of that previous one, or it is like this, same way like this. So it's 5. So that's why keep on increasing. So anyone try to apprehend how we can use recursion to actually solve this problem?
No.
So the one important concept recursion, which is one of the most powerful one, is you don't not try to solve the entire problem. You try to think how you could pass on the same problem, and in that case, you what you have to do, you have to generate the different shape. So you have to think in terms of binary tree. So what will have in binary tree? There will be a root, and this is, you can say, a left subtree and right subtree. So how you could you will think about only this root and then pass on the same problem to left and right subtree, right? So how you could make a difference so that your shape of entire binary will be always be different. So because all node are identical, so only difference what you could make, how many you say a node will you will send to create a left subtree, and how many you send to right subtree. So suppose you are sending x for left and y for right and 1 for this. So n will be, suppose this is rather than I write is left count lc plus right count and plus 1 root. So if this left and out count, these are different, because they are different, then they will make a different binary tree. So it is like, suppose n equal to 4, let's take the next, generate for the next one, 4. So if you take root here, so how many way you can differentiate? Left side you could base 0, so no node at all, and right side you can set 3. So it will make a binary tree which will have 3 nodes, 3 identical nodes. Let's have create a difference, and now you take root and send one node for the left and right. So it's, now you have only 2 to remaining for the right. So it will create a binary tree which have a 2 node in left. If you compare this, so they will always have a different shape, because in that case there is no left subtree in that, and right subtree have three node, and in that case left subtree have 1 node and right have 2. So they will always have a different shape, because number of nodes in left and right subtree are different. Same way you generate all the possible cases. Here you could send 2, and then here left is 1, and then just you send 3 left subtree and right subtree. uh, there is no binary tree in that, so all is it. So now rule is simple. If this is a binary tree, the same way come back to here. So if there, suppose this is a x way, you can create left subtree, and y way you could create right subtree. So there's x into y ways you can create the entire binary tree. So just apply this rule one by one. There are 4 different possible way. In this case, this empty, so there's only one way to create it, which we could say it is actually the value of 0. So 0 is like an empty thing, nothing is there. So the only one way. So this base case is f0 is 1, because we are multiplying. That's why it's a base case is 1. And 3, we already know the answer for 3 into 5. So 1 into 5 will be the this case, and then Just plus for this one, we already know answer for there's only one way we can create one. For two answer we know two. So two ways to create this kind, and same way 2 into 1 this, and same way 5 multiply 1. So we just have to do 5 into 10 and 2 into, so 14 is the answer for F4. So now you understand what we are doing. So rather than solving entire problem to generate entire, we know if how we could pass on the nodes to create the entire tree to left subtree and right subtree. So in that case, all nodes are identical. Only thing which will make difference is how many nodes you are passing in left subtree and right subtree. So our problem is limited to create to choose the root, and choosing in the ways how many will be in left subtree and how many in the right subtree. When the count is different, shape will always different. So in that case, only one there, left subtree have only one node and right subtree have two node. In that case, right subtree have two and left subtree, so they always have a different shape because in left subtree and right subtree count are different. So when we actually generalize this, hi, we are just discussing the question we have given for assignment. So when we generalize this approach, it is like we have n nodes, and we try to find out how many different possible way we can send an left nodes to left subtree and right subtree. So we can start having 0 nodes in left subtree and up to n minus 1, and same way right will automatically be decided because it will be n minus I if I is the left side, I minus 1, because 1 we have reserving for the root. So it's just suppose we are writing this program, so it's all or let's say binary tree, or binary tree, or you can say better binary tree from n nodes. Suppose this is the total binary tree we are generating from n nodes, and it is just taking integer n. So it will return the answer. So it's first the base cases. So if so initially the same way we will not fall into the mistake of minus. So first write that if n is less than 0, so we just return any value which we are not actually supporting. So minus 1, that will indicate it's a wrong input, just to handle the minus infinity case. Or our loop will also could have actually handle that. It will have a for loop. So is our base case n equal to 0 or n equal to 1? So we can return 1. The answer is 1. So at 1 and for n 1 is clear, and for 0 we are returning 1 because it's a base case. We could have empty left subtree or right subtree. For all cases we have a loop. Suppose we have a variable count. Count is total number of way we can generate. We start is from 0, and then we have a for loop. This for loop will select how many nodes will be there in the left subtree. So I equal to 0, I equal to less than n, because 1 we will reserve for root, so it will go up to I minus 1 and I plus plus. So total way we could generate will be count. So we will just add the new value into the count. It is the same binary tree from n nodes. Binary tree n nodes. So left side is I. So it's I, and how many nodes will be there in right side if left side is I?
N minus I.
And not n minus I. Actually, 1 we are reserving for root actually, no? So n minus I minus 1.
minus.
So does this, and this loop will generate all the value and we keep on adding here. So our total case we will count and just return this. So in that case, if we have actually, even we could eliminate this case also, because our for loop will not run in that case, because I values um, 0 or I should be less than n, and it will not be the case, so it will stop and we will return by default 0. So we could eliminate this also, but that's fine if we return. So this is the code. Let's think how much actually time it will take. So
Sir, can you explain why are we multiplying this?
yeah, multiplying is what we are saying doing. We have n nodes, so we are trying to differentiate how many different binary we could create which shape is different. So in that case, shape we are deciding how many nodes will be there in left subtree and how many in right subtree, like in the case. So in that case, our left subtree have a 0. uh, you, on we could write like this, and right have 3 nodes, and in that case left subtree have 1 nodes and right have 2. In left have 2, right have 1, either 3, and this have like answer 0. So in that case, our left subtree and right subtree elements are count is different and all elements are identical, so they will always create a different shape. So in that case, suppose we have a general tree in which suppose left I have given I elements and j we have right j elements, and there is x ways we can create a binary tree of I elements, and y ways we can create binary tree of j elements following the same rule. So total ways we can create this entire different binary tree is possible with this arrangement, in which left subtree could be, we could create left subtree by x ways and right y. So total will be x into y, right? Because every pair will create a valid binary. The same thing we discussed in previous class. Is it clear why we are multiplying the ways we can create left subtree and the ways we can create right subtree?
Yes.
Okay, so the same way we are doing here. So what this loop is doing is loop is selecting how many elements or nodes we are sending to create the left subtree. So in this case, I is for the left subtree, and this automatically be decided for right subtree, because one we are reserving for root, and so it will be n minus I minus I. So whatever, how many ways, these are the ways we can create left subtree, and these are the ways we can create right subtree. So we are just multiplying it. So that's why we are multiplying that get the answer for one case. When new case, when we increase the count in left subtree and reduce a count is right subtree, and then again do the multiplication and keep on adding. So we are adding all the value for all the cases. Is it clear
So
now?
one question.
Mm-hmm.
So one question. Cannot we run the loop till n by 2? Since and in the end we can multiply the result
Yes,
by
you
2.
you can do that. You can, because they are symmetrical cases, or you can actually do and just do the double. So that is possible. So I am not doing that a rate optimization, because using memorization we can increase this count quite much. So that I was not doing, but yeah, we can do that up to half, because cases are symmetrical always. You will find always the symmetrical cases like this and this symmetrical, and this you can see this. So you can just go up to the half and find the value and just double the count. You could do that. So now look about what is the complexity of this. So if we make like a tree of this, so if we're calling from n fn, so what is it actually doing? So it will call creating a multiple branches, and this branches, suppose left side it is calling for f starting from f0, right side fn minus 1, same way this way f1 and fn minus 2, and suppose the last one will be this side it will be fn minus 1 and it will be f0. right? So if we try to now, so other one we are calculating. So if we are calculating this, so basically branches are starting from every time starting from f0 to fn minus 1. So n minus 1 branches is being created. So so what we are doing, so every time, so if you think about this way, this will suppose n minus 1, this will again creating n minus 1 branch. So the branches is roughly equal, so up to this value. So how much value is there? So when we will, if suppose we are doing normal recursion and we are not memorizing anything, so what will happen, we will not start returning unless we reach this value, n equal to 0 and equal to 1. So level is clear. So in that case, it's again is have n it have from 0 to n minus 1, like n branch. In this case it have n minus 1 branch, and then again we'll have this n minus 2 branches. So how many levels will be there in this? So this is the first level, the second and third. So when we start this, we are sure that tree will not go on any longer. So in that case, this n is calling from n minus 1. So it will be here calling, will be calling fn minus 2. N is next this level, and next level it will be calling n minus 2, n minus 3, and this will go up to 1. So total level will be equal to n this way. So level, I am writing here, level equal to n, and branch is also equal to n. Every time whatever is the input, that many branches is there. So it's roughly n to the power n in this order. You can just write a little bit. My son is like that because every time you the is become n minus 1, so it's n minus 1 branches and then n minus 2 branches. So first level it will be increased by n, then n multiply by n minus 1, then minus 2. So it will like factorial n. So you can write factorial n also. So but order remain the same, n minus to the power n. So this is the brute force cases. So it's like if you started with n, so initially it will have n branches first level. Then this left one, which is actually n minus 1, so it will have n minus 1 branches. This all other also have branches but little smaller, and this will also n minus 2 branches, and keep on going unless you reach the value of 1. So roughly you can say any of this answer. So both are upper bound. So this is the brute force approach. It will take approximately n to the power n, or you can say factorial n ways. So so it is quite high. So how to reduce that? So what we learned in last class, to reduce the time complexity of usual recursive solution. Yes, tell me.
Memorization.
Yeah, memorization. If you see here itself, so let's see, in that case we have calculated value for f3 here, but here again we are calling it again. Same way for 2 we are calculated and then we are again calling. So this is just in that case, but it's recursively to, so we are calling same value again and again and again. So the simple way is just a normal memorization. So we will just do the memorization, and suppose we have integer results. So it will always work this way. We always check if that value is calculated. So in that result, suppose we have this array. So same way we fill the base value and on other value is negative. So if we want to calculate up to this 6, 7, 8, so we will fill these two values 1 and all values minus 1. So whenever in the rule remain the same. So from here, before we come here, so we will check if results less than 0. If it is less than 0, then it goes inside this, and it's count the value and everything. We are not returning it, but we will set this value. and always return value of from results. So in that case, whenever we do it, so what will happen? The multiples loop will go on. So let's take a concrete example and then see how loop will be gone. Suppose take example of F5. So here is this. So this side it is taking first F4, and this side is need F0, then F3, this side F1, F2, and F2, then F1, F3, F0, and then F4. So again, for this will have 4 value. So actually these were not created, but these are inside this for loop. So I could write this is for loop. We will call for this way. So F4 will in have 4. So initially when we have 5, we have 5 is not calculated. So we'll go inside this loop. Then 4 is also not calculated. So it will call for F3. And I'm just writing the left side value, right will automatically created. So F2, F1, F0. F3 is not calculated, F4, so it will also go inside loop. So this is also again a loop. So F2, F1, F0, and then F2 also not calculated, so it will also go for loop F1 and F0. If it so in that case, this is our base condition. Let's see how we calculated. So F1 is calculated, F1 is already there, so it will return. F0 already is written, so this is now calculated F2. So now we have a F0, F1 and F2. F1 is already there, so there is no need to call recursively. F0 is already there, so this value F3 will automatically calculated. Now so we have value for F0, F1, F2 and F3. So other, if you write what other is needed, so it's needed just 0 here, and for one value it's already, so all value we have there whenever we calculated leftmost value. So F1 and then F2 and then here F3. So you say all value we are available here, whatever we needed, if we have up to F3. So no, there will be no you branching for this. All value we will get from this array. So this for loop will run, but all value will get from this array, and now we will calculate F4. Now we have F4 also. So now you will say we already have this. We have this F3, F1, F2. We have all these value, whatever we needed. So then we'll calculate F5. So this will be what is happening. Again, the branching has entirely gone. You can say there's only one branch, but this for loop will remain. So because we are when we are calling from Fn, so all the value from F1 to Fn all will be calculated. F2 will be calculated through a loop. Then F3 will be calculated through a loop. F4 will calculate through F5. So now can you tell what will be the effective time complexity now when we use memorization?
F of n.
Mm-hmm.
O of n, sorry.
So there is a little catch here. It's not exactly oven. Reason is that let me explain here. So because the for loop is there, the region. So when initially we will call for n, so fn is not calculated. So it will be calculated only through the loop. So in this loop, even though all the right side value we will get from array, but this loop will run. So this for loop, what we say, this for loop will run n time. So because its length is n, and then the leftmost values are to calculate it again by the for loop. So this is again a for loop in next level, and the length of this for loop, you can say n minus 1, and then left side, and this for will again will calculate it by for loop, and that's its length will be n minus 2, and this will keep on going up to this. So you can say all these value are getting from the array, and this value is calculated from the loop, and so every level one loop is running, and then next level all these value getting from the array, but loop is running. If you think about this first time, so this at this level the cost of running this loop is n, next level running of cost this loop is n minus 1, next level is n minus 2, and you can see how this is happening. Though is this level we are calculating fn, and this level we are calculating this n minus 1, fn minus 1 if we write this properly, and this level we are calculating fn minus 2, and you can calculate it this only through the loop when all the smaller value have already been calculated. So the every level the cost of this is basically n minus 1 minus 2 minus 3. When you add up all these costs, it will be like sigma n. You can say next is level 1, next level 2, 3, and up to n. So it is, so sigma n, it will go into the level of n square, n into n plus 1 by 2. So level is n. So now cost is n square rather than on, and reason is that because we have a loop in this. So if we go through this, so whenever we try to find out what is the cost of this, so we say this is all o1, but when this loop is there, so cost of this segment, this is itself on, whatever is the value we are calling. So our cost of this method is not o1. If cost was o1, then we could say that there is only n level, and so every level we are returning all the value from the array, so it will be o1. But every level we, even though we know all the values, suppose this there we want to calculate it n, and for this we are running this loop, even though we know all the value we will need it here, we will get it from the array, but still this for loop will run. So one for loop will run in every level, and the level remain the same n. So answer will be n square. Is it clear how time complexity is on square after memorization?
Yes.
So this is the important difference you want to understand. When there is a loop in a for loop, so your cost even after memorization has to be included that loop. So because one single call, whenever this method is running, that loop is running. If you do one thing, this also you cannot calculate it fn unless you calculated fn minus 1. So for calculated fn, your cost will be n. Calculated fn minus 1, your cost will be n minus 1. When minus this cost you have to bear, then only you can calculate it fn. So it will again the segment. So okay, let's discuss the old thing. What will what is the space complexity? Say space complexity depend upon the length of stack trace. The longest stack trace will be the method, you say method stack. So how long will that be when we are calling this method? So in worst case, how long that method call stack will be?
Number of levels
Order,
that there are.
order of n?
Yeah, order of n itself. You look about this. So when you are calling for fn, so if you are calling here for fn minus 1 is not calculated, it will be on top of that. Then fn minus 2 will be top on that, and minus 3, and it will go on up to f1. So then only we'll start returning, and so if before start returning, we'll call up to n, and there will be n method on the stack, so it will remain o1. So in most of the cases, your stack, whenever you think about space complexity, just think about how many levels will be there in your recursion tree. So that is directly equal to your space complexity. So it will remain the same. So is it clear?
Yes, sir.
Okay. So let's move on to recursion. Others things where recursion is heavily used, usually like to generate different kind of cases and selection, uh, usually the brute force for many solution. So before moving that, let's discuss the other assignment we have given in last class. So whenever we do the memorization, if this was the grid, and we are doing either right or down, and we were starting to memorizing. So it is like, suppose you are here, so it get call from here, or it could get call from here. Same way for everyone. But we started memorizing this thing. So what will be the time complexity? So it's like we are starting from here. It will call here, and it will call here, and the successively it will call every point unless you reach here, then start returning. All outside, you will immediately return with zero value. So what is the time complexity when we started memorizing? And recursion is was this f.
Here,
Hmm.
order of nm.
Yeah, order of mn. So
Yeah.
so let's just, it was, let me write again, f I j minus 1 plus f I minus 1 j. So if we go this way, suppose we are not memorizing. So what is happen, this is inform 1, this 2, but when we come to this, it's get call from here also and here also for 2 times. And for suppose this point, it is getting call here also and here also, but this calls is also getting multiple times. So if we look come out with this call, so it's getting call from here and call from here, but how many times you will call it, that many time it will call this. And this is getting calls from here also, and this is also multiple. So in this case, it's keep on increasing exponentially whenever you move this side or this side. So what happened when we started memorization? So what happened if, suppose this call is getting multiple times, but when we started memorization, so what will happen? Suppose it's getting in this case every is getting 2 calls, but in that case, even though getting multiple calls, so it only for the first time it will call these two value. And next time whenever it get called, suppose it get called first time here and it call this and memorize this particular value. So next time when it will get call from this side, it will not call then successively. So whenever you start memorization, so what will happen, any values, suppose this is the value. So first time suppose get call from here and is this value get memorized. So next time it will get before is returning, it's also have memorized this value. When it get call from this side, so it will return the same value and it also memorize that value. Now what will happen, so any of these if get the call again, suppose first time it was getting call from this side, from here, and from next time this is getting call from here. So this time it will not call again this because it's already have saved its value. So in this case, and same way, suppose next time this is getting call from this side, so it will not call this again because it's already saved its value. So what will happen in that case, every point which can say Fij's method get called only by twice, either this way or this wise. And first time it will call is in this two direction and save its value, and next time it will return its save value. So but not more than 2 calls. So every calls which you can distinguish by ij get called only by twice. If this entire process, you know that every call, every unique ij call will be called only twice. So total calls you know immediately. So there are total m into n, so m into n, so and or n into m is the total different possible way you could call the same recursive function, and every call you could call only twice. So usually 2n. So these are the total number of calls, and every calls is taking O1 time. So total time remain OMN. So this is the way you calculate time complexity in top-down dynamic programming. When do a bottom-up is clear because to fill every point from left to right is just taking O1 time. So this is clear in dynamic bottom-up DP. So but that we will discuss later when we discuss dynamic programming. So
So
yes.
how we'll do if we wanted to do it like branch to the power level method?
Branch to the power level is when you are not doing any memorization. and
Okay.
you are doing usual recursion. So in that case, you know that every time you are running a recursion, your branch is getting created, and one call is converting into that multiple calls. So you can directly multiply branch to the power level when you are not doing memorization, and cost of your recursion method is constant. So it's not dependent upon the input, which input you are passing.
Okay.
So we will do some other recursion, in which case cost will not be constant. The usual example is merge sort. So we will discuss those examples. So let's do the similar kind of problem, but one which are more little bit more popular. So you have this array. Let's otherwise you can use this example itself. So in that case, you have the similar kind of direction. You can like one more direction you can move diagonal also. So but here every time point you have some coins, like here 4, here 2, 1, 10, 3. For this, and some points could have like hurdle also or other thing. So suppose first this is like 4. So you are standing here and you have to reach here, and every time you have a 3 direction. It's like then down, right, or diagonal. So what you have to do, you have to tell if you are starting from here and taking direction either down, diagonal, right, what is the maximum coin you can collect when you reach here. So some points you could have coins in negative itself, or some there will be some points which is like hurdles where you cannot go. So we will extend that thing later. So initially suppose there are all this value and you are standing here, and you have to find out what is the maximum coins you can collect when you reach here. So how you approach that question? Just tell me how you approach.
So, so we'll consider all the three ways and also keep score of their counts, like on
Mm-hmm.
which path what score we are getting.
Mm-hmm.
And then when will do backtracking, and then when we'll reach 0 0, we'll see from which way we have got the maximum score and can return that score.
Mm-hmm. So if we just explain what you are saying, so it is like every point, suppose we are reaching this point. So we again think about the recursive way. So we have only 3 way to reach it. So either we could come this way, or this way. So whenever we are thinking about how much coin we can get when we reach here, so whatever point coin are there we will get, either we are reaching from this side, this side, this side. So it is not affecting our judgment. Only if we are coming from this side, we'll think how much coins we could have if we reach here. If we reach here, if we reach here, all 3 are valid way to reach here. So we will reach from that way where we already get the maximum coin. So in that case, because whatever coin we are here, we will get automatically. So in that case, when we converted this recursive equation, so it will become like this. So in and this also. So we want the maximum value to reach ij. So we will reach from maximum of all possible these values, I minus 1, j minus 1. And whenever we reach it, we will already get whatever, suppose this is array have this input, I and j. So what is doing, this is actually this way, so I j minus 1, that's mean last move is right. And this is I minus 1 j, last move is down. And this is diagonal. So out of these three, we will select which already have the value of maximum. So out of three values, we will select the maximum. So whatever is the maximum out of these three, that we will select to reach this point Ij, and then calculate whatever is the maximum up to that value, and then we will add this value to reach this point. So this only we will do in the recursion. So we'll start from the last point and just write the same way we will return. So again, because we are calling this way at the introduction, we could go outside of this grid. So that will handle, again, in previous question we are just returning 0, but in that case we will return a different value to handle this max condition. So we'll just tell how to handle this max. Just give me a minute, just come back. Yeah. Um, so in that case, let's just write this. So suppose this code is to get max coin. So in that case, initially we will call it from this point because we have to reach here, and this is our starting. So in that case, we're starting. So it could be given some coins, whatever there or not be. So based on this array value, so we'll call from this value. So starting from I integer j. So I think that, and this array input array. Suppose this is here. So same thing, the base condition. So one thing, if I is less than 0 or j is less than 0, that's mean we are calling outside of this grid. So there is no ways you could come outside of this. You cannot come from this side, or you cannot come from this side. So what we should return in this case? Just tell me. So let me tell you the basic rule whenever we are writing recursion for maximizing something or minimize something, and we want to discard some particular uh, selection. So in that case, we suppose we are here, we are calling these two value. We know that we cannot come from this value, and we are trying to maximize. So whenever we are trying to maximize, our default way which we want to reject is will be minimum. So a big minimum constant. So this is a constant, so like a big um, minimum value. So we know whenever we have a maximizing this, we will always reject this. So in that case, if we are here, so we are three value, this will be outside, this will be outside, this will be this inside grid. So these two value will return min. So both will be rejected because other value will have some value which will be selected by the max. So whenever you are maximizing, your default will be rejected, one will be min, and we are actually maximizing, minimizing, the default will be max. So this is the basic rule whenever you are trying to optimize anything through recursion. So this is our default value. Otherwise,
if you return 0, will that be a problem?
yeah, that could become a problem in which case there will be negative values. So any negative values. So the basic rule is always uh, uh, the always return minimum value when we are sure that all value are positive. If all coins are positive, so in that case you can use 0. So, but even if you use this min, it will work in always case, like a generic example. When you are maximizing for discard value, return min. Whenever you are minimizing for discard value, return max. So it is independent of then you become your input. So which kind of this thing. So if there is a negative value also, it will handle. So otherwise 0 will work only in positive cases when you have all value positive. We will do a little changes whenever suppose we have to handle the hurdles, another thing. So the same way hurdles will also work this way. So I will explain. Suppose first complete this. So other than this, where not what we will do, will return and whatever is the values this point arr I j plus the max of get max coins, and this is like I minus 1 j or get max coin I j minus 1 or this I minus 1 j minus 1. So this is the way. This way we will just return the maximum of whatever these thing and just add this value. So this is the case. So now suppose interview has said there are some hurdles where you cannot just reach. So it's like in initial this way it will like cross out something. This you cannot reach, suppose, or like you cannot reach this value and you cannot reach like this value, right? Suppose. So these are like dull you cannot reach. So how to handle these things so you cannot reach that value? So the same way, so you want to rule out that value. Suppose you are here and you call these three value, you want to rule out this value, you cannot just reach here. So in that case, so the same way how we are actually handling, so we are maximizing something. So if you want to rule out something, so we will actually in that case we know that we cannot come from this value. So for whatever whenever we have are actually maximizing anything, so in that case we will return if we will make this value as min, this as min, so it will be automatically minimizing, so we cannot come from these values. So in that case it is like whenever we are calling from this doing this, yeah, this. So if we make this value for that value as a min values, so what will happen? So in that case we will make this value make like a min value. We just replace this value as a main value. So what will happen when there's vehicle min value? So it will save that value as a min. So whenever you are calling it from here and here, so for this it will automatically be this value will min. So whatever you value will add it, it will again remain the min. So in that case it will never be calculated. So whenever you call this value, so it will call this and this. Whenever you have already assigned this value as a min for this, so automatically calculate this value as a min. So out of these three it will never get calculated. So a single way to handle hurdle is that, so just replace all the hurdle value whatever is there by this min. So just only this you have to do, nothing else, and then it will automatically calculate, because whenever it will calculated this value, it will always be calculated min, because it will be adding min to that value, or min is like a minus 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 something. So it will, so it's automatically, so whenever is the case when you are exploring the grid or something and this uh, this thing is there like hurdles. So handle hurdle is the same way. If you are maximizing something, just replace the hurdle with min, and if you are minimizing something, just replace the hurdle with max, and this program will automatically take care of everything else. So this is the case. So you will replace this and all the hurdles by min value, and automatically program will handle that thing. So this is the way we can do this thing. So interviewer can do many changes as you will, if you are doing this correctly. He will say like it's not like you're just collecting the coins, but taking steps will also take cost. So it is like writing, if you take right is take one coins, you have to spend 1 coins. To take downs you have to spend 2 coins, and take diagonal you have to spend 3 coins. So these direction movement have a cost. Right 1 coins, diagonal 3 coins, down 2 coins. Then you have to maximize what is the maximum coin you can collect when you reach the last value. So how you change your code or your recursive relation for that? So this is our recursive relation. What change we have to do in this? If the every step have a cost, right? It cost 1 coin, down 2 coins, and diagonal 3 coins.
We'll have to multiply this the direction cost with the movement cost.
So not multiply actually. So because whenever we are taking direction, we will have to
And
spend
it,
that coin. So we have
oh,
to. So in that max, before that, whatever it is the cost, how much we will get from reaching here. But now it's included in the moment also. So before comparing for max, we will reduce that coin, because if up to this point we can get suppose X coin, but when we reach this point we will have to spend 1 coin, so it will be -1 actually. So when we will reach that point, and then this down, if we have Y coins we can collect, so up to when we reach IJ it will be Y -2. And same way if this is a Z coin we could collect and we have to take diagonals, it will be Z -3 actually. So that we have to include here before comparing. So it is like -1 before compare, -2 and -3. That is the only change we have to do. So because we know we have to spend 1 coin. If we are coming from right, we have to spend 2 coins and we have to spend 3 coins. So we have to spend 3 coins. So before that, if you get that and then -3, then only we will compare which is giving the maximum, because we will that coins we will always get, so it will remain outside of this. But for inside we have to just adjust these coins we have to spend, right?
Yes, sir.
One if we implement that thing here, so this way actually interviewer make it a little bit complicated, one bit by bit. So in that case, this is which one case it's coming from actually, right? So -1, it's coming actually down, -2 and diagonal -3. Okay, so in that case sometime it could happen uh, like you cannot reach a particular points from here because anyone after this will become 0. So 0 is like that you cannot, this point is reachable from this direction, right? So in that case, or if you are supposing you are, this point is not reachable, because here suppose you got from 1 and from this, so it is not, suppose here it is giving only 1. So it is reachable only from this direction, so you cannot come and reach this. So it could happen like some point could become unreachable by this. So you cannot reach this point because this will take 2. It's 1, this right is 1 and down is 2. So suppose it's okay, let's me just make it little clear first. Okay, okay, let's make that scenario. Right is taking 1. Okay, so let's this is make it 1 only, then let's make it 2 here, and then it is like 1 and 2 and then 15. Okay, and then it's like 4, 3, 6, 5, 2. So suppose this is the case. So initially suppose here only 1 coin is available, so you cannot take this direction too. right? And in that case, or you can do reach this and this way. So this in that case, if you cannot take this direction, so this 15 is not reachable, because you can reach 15 here only. But if you will calculate this thing from this direction, so what will happen if you are calculating this thing? So in that case, it will call this and this also, and this will call this and this and this also. So you have not created any condition in which actually you are selecting only the max. So what will happen in this direction? It will min, and this will be actually 1 minus 2. So that will minus 1. So even if it is minus 1, you will select this value, and that value become here minus 1, and in that case you will select this also. But in actual condition, this is unreachable, you cannot reach this. So if you are not handling this condition, you are selecting minus value because other values even is smaller. So what will do, you will reach this, and your answer will be somewhere getting from this direction, like this, because this is giving a positive. But inside this, here to here, using this role, this point is actually unreachable, you cannot reach here. So in that case, what you have to do, so whenever you in this, the maximum thing you have to do, so in that case, the point is whenever this point after this, it is become 0, so that point is actually become unreachable. You are getting this point? So in this, when we are writing this, so rather than writing this itself, so whenever we are calling outside of this, so that is handling properly, because we are returning min, and whatever we will add or delete from min, it will remain the min. But if that value is not min but particular value, but after return this value minus 2 or minus 3, it will become 0, or you say less, 0 is fine, less than 0. So that's mean you cannot come from that direction, you do not have sufficient coin to come from that direction. Is that getting clear what I'm trying to tell?
Yes, sir.
So it is like you are, let's take a generic position, you are here, and you could come from this direction, you could come from this direction, you could come from this direction. So suppose you have these coins, but after spending 3 coins, you actually effective coins is less than 1, like minus 1. So that is saying at this point maximum you could have like 2 coins, but spending 3, this will now have minus 1. So you cannot come from this diagonal way. So diagonal case is not actually valid. So to avoid those cases in which you actually cannot have you cannot come from this direction, because that could create problem, because you cannot come from this direction, this have only 1 coin and this take 2 coins. So you, if you keep on coins, so suppose this is very big value here, like 500. So in that case, if you come from this side, you will get this coin and automatically, but actually this path is not available, because this is not actually you can reachable point from this in terms of this coin. So you should mention that you do not include those thing in that case. So how to handle that thing? It is like so problem get clear to you if after some, after this plus or minus, if that value is getting this entire value is now getting negative, so you cannot consider that value even, and that will create problem when other problem is far more negative, like you are calling outside. Let this, in this case, suppose you are calling, so you are calling this, and the other thing is that already you are calling outside of this. So outside is minimum, this is outside minimum, so this is remain minus 1, but still it is the maximum value, so it will select that value. So we are not ruling out that value in which actually we are calling a value which is actually negative. So how to handle that thing, can anyone suggest, so that we could never consider those points which are unreachable? Any suggestion?
If our value is negative, we will return a min only.
Yes.
We'll check.
So this is the common way. So in that case, when you are maximizing, all the value which you are ruling out will always be handled by men. So in that case, again, what will happen? we, instead of this, we can just get this value. This will, you can say, this is which side we are coming, is right, it's down, diagonal. So if that particular value is basically negative, so instead of that, we will get that value as min whenever that value become negative. So what we will do, so we just make this, so we could have three values here. So suppose this is right value, so we will assign, so we are just make returning. So we will first find three values. So this is right value, right side. So we will compare this value. If this value is not less than 0, you're greater than or equal to 0. So it is greater than or equal to 0. So it will remain fine. Otherwise, we will make it the value. Let's rather than first take its value and then change. Otherwise, we have to write it 2 times. Suppose it's right. Let's give right as this. So it could be minus value, right? So we just write, or we can just flip this value. So if right is less than 0, if it not less than 0, that's fine. If it is less than 0, then we will become this right equal to min. So this is right. So let's make capital right. So we have to this, if this is for right, and same way we have to do it down and diagonal. We don't know which will become negative, so we will do it for all the values. So this is the way how you handle, and this is for the down value. So we will assign the down value, and again way, if down is less than 0, then down will become min. So you have to find out this way how you will handle. But main concept is that when you are maximizing your default value, to discard is min, and same way diagonal. So it usually most interview do not complicate, but if interviewer had time and you solve this quite early, so he could a little bit started complicating. And the main thing they want is that you can handle all the cases. So in this case, if you do that, and then after you will apply the same basic rule. Return what with input ij plus max of. Now if you are converting it to min, then max will automatically discard it. So when all three will be min, max of 3 will be again be min. So automatically entire value will be min. So it right, down, diagonal. This way, and then you just return that thing. So in that case, what we are doing, so suppose take this case also, it will give -1 value. This is already min and min. So what we'll do, we will make this value as a min, other are already min, we are getting from down. So all three value will be min. So it have to select the min itself. So this plus this will become the min. So this value of this point will become min. When it will become min, it's become unreachable. So you cannot come from this point in same way. So we are actually avoiding all the points which are unreachable. So this way we keep on we handling these things. So in that case, we understand how to handle when we are reaching outside. So that is we will handle through min. We handle how to handle the hurdles. So all the hurdles we have to just fill with the min. And then we understand how to handle when there is cost associated with every move, and there are some moves which after getting the cost become negative. So again the same way, so convert this value into min. If that after detecting the coins, it will become total become negative, and then you apply the same rule. So is it clear now?
Sir, one question I have. For example, can you go to that grid once?
Yes.
So in this grid, for example, at 0, 0, we have 1. And if we go down, let's say towards 500, but we want to take that path, right? Because that is giving the maximum result to us.
Yeah, so if that is giving the maximum result, but legally we cannot actually take that path. You think of that. So here we have one coin. So one coins, we can go this right and this here. We cannot take diagonal. This is off limit, and this is off limit. So this path is legally not available to us, because this is the rule. We have to, if we are going right, we have to one coin, for down 2 coins, but there's only one coin. So only through this way you could go. So here you can think going this way, or this way. Again, diagonal is not available. So legally it's not available. This path is not available, but our algorithm do not know. So it will consider that, because here it will become negative, but here out down this is a big value. So it will consider this way, but this is not a legal path.
Right. Correct, sir. Thank you.
Okay. So this is the way, just how do you handle these kind of things. So that is just to explain. So again, the complexity is high. So can you, if you roughly, can you tell how much be the depth of your space complexity? So how depth will the level of it? So how many the value will be there in the recursion stack in the worst case? So rule is simple. If you're starting from here, so you will start returning if you reach this point or this point. So the worst case you needed to reach this point is the longest. So just think about, if you're going think, then there will be little in the recursion and you reach the last point. But this direction, if go this direction and then go this direction, this is the worst case. The longest will be the your stack, right?
I plus J.
So yeah. So if this is m into n grid, so it is m into n, right? So in that case, your space complexity is O. Sorry, m plus n. Sorry, I wrote it wrong. So not m into n. So it is like m into n the great size. It is like in that case you call this, then you call this, then this, then this. In that case, you if you call outside, it will immediately turn here. It immediately turn. You will call this. So this call will be on top of the stack, and this is the worst case. And after this is must return either this or this way. It cannot go, because there is not, you cannot go circular, because you can always taking in this direction, these three direction. So this is the worst case. M plus n. Sorry. So m plus n is the worst case. Your stack, the longest your stack could be. So this is your space complexity. If you are not doing anything, in roughly you can say time complexity is, because you have branches 3. So 3 to the power m plus n. It will be little less than that, because every time this is the worst case, but every time you will not have 3 branches. But roughly you can see, because this is the upper limit. So that's fine, because you will give the solution of optimized solution. So how to optimize? There's only one way to optimize this kind, because whenever the value is fixed for a particular value, we know how many coins we will get from IJ. It is fixed, because no matter how many times we call this method with this input, it will always give the same answer, because that value is fixed. So we just memorize that. So whenever we started memorizing thing, so what happened? So just focus on a particular one call. Suppose this. Again the same logic, it get call from here, get call from here, get call from here. So when it get from it return, it will save it value, then it will also save it value, and it will also save it value, right? So in that case, if this is getting another call from this side, it will not call again. Same way it is getting call, it will not call again, it will not call again. So every point which say Fij will get call only from 3 times, not more than that. Even if one time it will call is this in 3 direction and then save its value, next 2 time it will return the same value. But we are counting the how many times we are getting a calls. If you think about this, so everything is O1, this is O1, this everything is O1. So everything is taking O1 time, no loop and nothing any. So actually our method is taking O1 time, but it's only do just recursive call. So we have to calculate how many total calls we will make. And when we will do memorization, total calls will be just 3 times of all possible calls. All possible call is m into n, and only 3 calls will happen for one value because we are saving. So it's 3mn, and it will convert into O. This is our time complexity. Is it clear?
Sir, can you explain once more?
So what we are trying
3mn.
to do, so we are actually here doing again we usually do the memorization. So we will do a same thing for memorization results. Well, yes, results, and then before that we will just check again if this answer is not in results. Results I, results j is less than 0. Initially we will fill only the first value, the first point. If it less than that, then we will calculate. So just returning, we are just fixing that value, and now will become memorization. And we always return that value. Result. So in that case, now we have everything is inside this if, and only if it not calculated, then we will calculate this. So what will happen, take any point, suppose this point is there. So first it will get call only from here or here or here. Only 3 type of call is possible. Suppose is get the call from here. So this time it will call successively its children and then return. So it will return its value and save its own values. So and then it will return, it will all, when it's all other call return, it will also save its value. Then next time suppose it get call from here, so it will not call its children, immediately give its value, and when it's written it will again save its value. And then a third call for this, it will is have already saved, it will return, it will also save its value. So it gets 3 calls, one calls from this, one call from this, one call from this, because once which is calling also saving its well call, so it's not the same thing, it will not calling it's again. So what is happening, suppose this one first time getting call from here, next time it's like getting calls from here, so it will not call again because already saved it value. Same way if this is getting calls from other side here and here, it will not call again because already saved it value. And same way this will getting calls from here, this will not call again because already saved its value. So what happened, every point will get only 3 calls, because one calls from this which is for right, one is for like down, and one for the diagonal. So but it will actually because whenever each return is saved their own value, so they will not call again. So every point will call the another points only once, and we know that any points will get point 3 calls from 3 different points, not more than 3 points, only 3 points. And because of this memorization, we know one point like this point is calling this point could happen only once, and same way this point, so this point and only once. So if every point, this is actually this point will call 3 points, but if we think opposite, how many different point will call this point, this will be only 3 points. So every point will call only once, so total calls every point will get 3. So we know no matter how this will run, every point will not get more than 3 calls, right? So total calls will become 3mn. Yeah, we have written. Is it clear, or just explain it to make a clear grid? So let's me make it's a generic case. Just make a small grid, just simple example. Suppose this is somewhere in the grid. So this is I and this is J. So who could call Ij? Either I plus 1 or J plus 1, or I J plus 1, or I plus 1 J. Only 3 could call this particular value. If you are looking for this guy, so only either it could be called by this, or this by this, or by this. No other can call it directly, right? So what happened, we are getting too much complexity, because this guy is getting multiple call and this guy is getting multiple call, this and every time it is calling this. So what happened, after memorization, suppose it's getting call from this, it is written this call, so it is saving this value. So when it is saving its value, when this guy is getting another call, suppose first time it is getting call from here, next time it's getting call from here, so it will not call this guy again. It will return whatever is have already been saved. Same way it will get another call from this, and this guy will also save its value. So next time it will not call again, and same way this guy will call it, and when it will return, it will save its value, it will not call again. So because of this memorization, any point ij get get only one call from another point. So this point can do only one call, same way this point can do only one call, and same way this point can do only one call, right? So only point is, so every point could get only one call from the other points, and only three possible points can call it. So that's mean every method fij could be called only by 3 times. So this is one point will be called that method. So how many different points are there which will call, because every different points represent one method call. So there are total ij m into n points, and every points will be called maximum only 3 times. So we are looking for max, we are assuming every point will be called by 3. So this will be 3mn calls will be there. Is it clear now?
Yes, sir.
Okay, so don't worry, we will do it again and again when we, especially when we do dynamic programming, it will become very cool. Now we are just actually doing recursion. So, but still we need to know when we do memorization, how things get improved. Okay, let's do another question using recursion. So this is one another popular question. So suppose you have left and right parenthesis. So suppose one left and one right. One left and one right. So there only one way you can make it correct this. So there is one way you could make it correct way. If you suppose two left and two right, it is either you could make this way, this is a correct way you can make parenthesis, or it's like this way. So there are two ways you can create correct order of parenthesis. Suppose it's three left and three right. So it could be like this is one way, or it is like this is one way, or it is like the mirror image of this way, or it is like this is another way, or it is like yes. So these five are all valid ways you can make left and right parenthesis, right? Is it clear? So this value is 5, right? So you have to tell this is for fn, what will be the for fn. If it is think this is for f1, f2, or you could actually have been printed interview tell you have n left parenthesis and n right parenthesis, just print all the valid permutations, valid way you could arrange this. You have to actually print that thing one line by line. So this could be the any case. So you actually have to generate these valid parentheses for n left and right. So how to do this thing? So this kind of problem is there where recursion will help you to generate the different cases, all different cases. So one way is just to keep generating either left or right, or to filling all the values, and after you finish it, you check if whatever case you have generated is actually valid or not. When it is valid, you print or increase the count, otherwise don't. But that thing is like initially fn equal to have 2n entry and left and right, and every time you could write either left or right. So its total generation will be like 2 to the power n to 2 to the power 2 1. That many different possible case you could generate from n left and right, and very few of them will be the valid cases. So we actually will generate so many cases, but very few will be the valid one. So it will usually time out this kind of solution. So we will try to write a solution in which we'll generate only the valid case. So how recursion we use to generate a different selection. So just write the code for that. So in that case, what we'll have, we will have a actual array in which we will write either left or right. We can have character array, or we could generate it through the rules. So if it is valid to keep the to take uh, take the next one as a left, so then we will otherwise take the next one as a right. So it is like a valid parenthesis. So in that case, we will just have a number. So in character array, suppose we have, in which we will have generate this character array size is 2n. So it is suppose a selection. And so whenever we are generated, suppose we have generated up to this far, and we suppose this we have generated, and we have generated up to in a valid way, and we have to generate it here. So it could be either the left one or it could be either the right one. So what is the rule which will tell us can we generate left here, or can we generate the next right here? So what is the rule, so that we know that when we generate it and up to this, it will be, this prefix will remain the valid, so that we are not, because it is like, suppose we have generated this right. So no matter what you generate after this, it is already invalid up to this point, because there's 2 right and 1 left. So whatever you generate, its entire thing will remain invalid. So always generate a valid prefix, right? So in that case, if you have generated this so far and this is generated properly, so what is the rule to select left or right in for the next?
So if the previous one is left, then it should be right, or the first one is left, then it should be right.
Well, not previous is not actually will tell it, because it is like this way. So previous is right, but next could be right. So it is like it's up to this how many left you have generated. So suppose we said, suppose this is it is telling index how many actually we have at which point we are generating, and this is like total n we have to generate, and this point is, this is important. So either you suppose you have generating for index and starting from 0, so you have already generated up to index, so you have to find out how many you have generated. So rule is simple, you can always add left value, because left is not violated anything. No matter, suppose this is a structure, this structure, you can always generate it left if left is available. So in that case, if how many you have left you have generated is less than n, then you can add left. So the rule of left is simple. For right is that whatever you have generated so far, if there is surplus of left is there, so that there is left should I, then you can generate the right, like you can generate right, or if this is the left or you right, so you can generate the right, because left is more than the right. But if left surplus is not there, so it is something like this. So you cannot add the right here, because only that many left is there, that many right is there, so you cannot that's mean your left surplus should cannot go in negative. So left surplus is already 0, you can say. So you cannot add the right. So rule of right is that. So left rule is simple, if left is available, you can add, you can always add left. But right you can only add when the left surplus is in positive, then only you can add. So you in important integer variable will have left count, how many left you have generated, you can say left count. So what this thing is doing, so it will return the total valid count also, and it will also generate print that value also. So this is the selection in which actually we are generating value, so that we could print that. Index is saying if suppose we have to generate these many value, so which one value we are generating. If index is there, that means that one we have generated uh, so far, and next one, this one we are generating. So index will tell us that, and n is just the input, so how many left and right we have, and this left count is how many left value we have generated. right? So this one we will keep on generating. So whenever we this index will starting from 0 and keep on increasing and become into 2n. So that's mean it have already generated 2n, and now we have successfully generated 2n values. So then we will print it. So if index greater than or equal to is, you can just say 2n. So equal to is also, because it will never go more than that. So here actually we will print, suppose this was print method, print selection. This is our method which will print the selection. We can pass it 2n, that up to 2n we have our answer. So and before that, because we have already generated everything, we just return. This return will tell this is the valid selection we have or not. So this is the valid selection, and we just return 1. So 1 valid we have generated this far. So before that, and it will actually get calculated. So we will keep on adding this value. So this is the valid. So all valid we have to count, return how many actually valid selection we are generating. Other than that, we have a two thing. We generate left, try to add left, or try to add right. So in that case, before that we can have a count initially equal to 0. So let's see if we can generate left or not. So what is the rule for generate left? If that mean left is remaining, so whatever we have generated left is less than n. If left count is less than n, so that's mean we have generated that left we have added, but it's still is less than n. We can generate more, so we can just have generate. So what we'll do, we will selection, we are generating for this index, and we will give it left, and then we will just call for the x. So co count equal to the same method, valid parenthesis. So in that case, selection, and now we have generated for this index. Now we will increase value index plus 1. So it will generate select for the next index, and remain the same. Now we have generated left, so left count will increase plus 1. So what it will return? It will return all the values which you could validly generate when you generate the left count for the index, and all the successive it will return, and then we will add all the valid one we will add in this our count. So this is the thing. So whenever you are doing selection through recursion, so whenever your recursion returns, so you always have to uh, undo your selection, because at this point now you have to do the other selection. Now you are adding left, so you are adding right. So you always have to undo the recursion, is the basic rule. But because we are doing in this array, so we could simply override it. If you are doing, if you are adding in this in any list, so we have to remove the last element, and then we can add the right. So but in array we could override, so we are not doing explicitly undo, but it will override this value here. So next time, now we try to add right. So what is the rule for the right? What we'll check, we can add right only when there is a left surplus. So how we'll check that? If we have these 4 value, left count so far and indexes, so if you are actually start filling for the index, that's many is starting from the 0, so that total you have been filled is equal to index left and right plus. So how many right is there? So left count is greater than, if left count is greater than, how many right is there? Right will be there is like index minus left count. That many right is there. So if left count is greater than this, you can just move it here. Your two left left count is this left count. So I'm making it clear that's this way, so that you know that these are the value of right count. So this is left count and this value is equal to right count. So how many right we have actually, because index we are filling at the index and starting from 0, that means total left and right you have filled is equal to index, and that many left we have filled, so this is equal to the total right we have filled. So if left field is greater than the right field, so filled so far, then only we can add the right. So we will add that right. So is selection, we will fill the right one, and then same way, just equal to valid parenthesis. Selection is index plus 1, then n, and now in that case we are adding the right one, so left count remains same. You can have separate left right count, but only one variable you can find the right count, so I've used only one variable. So if this is the case, now we have added left also and right also. There's no other way we can do. Now we just return the count this way. So this what it will do now, this is actually we are using recursion to generate all the possible selection, and rule we have already been applied. This is like a selection, select the left. So we have a rule is here, so can we select the left? So we are through rules we select, if possible we selected and call the next one. If we cannot select left here, so it will not call here, and the count will remain the same whatever is there. And this point, we are rule for the adding right if right is there, and then we increase the count. So count will indicate here, if we are adding right here, then how many successful we can add successively. So in that case we just then return the count. So just do a dry run for it, then it will become understandable how we are actually generating. Suppose we will take 3 for 3, so 3 left and 3 right. So initially all is empty, right? And we will call for this, right? So it will become a little bit bigger, but okay, let's find that. So in that case, we will have two branch. One will generate left and one will generate right. So left is valid, so we will right call the left. So 1, 2, 3, 4, 5, and 6. So here left we have added the left. So we will try to edit the right here, but through the rules, suppose this is left and this is right. So right we cannot generate, so it get cross out because there is left surplus is not there, right? So or we could write pass it that what value we are passing it. So in that case, index is we are passing it 0. First value is index, and the total value is always 3. N is 3, and the left count is 0, right? So in that case, if we get this 3, 0 is left count minus 0 minus 0, so it's not more than, so right we cannot fill. So this branch, there will be no such branch here. So now it will get here, then again two branches. We next level will try to left or try to right. So in that case, when we fill this, the value of this value, it will become 1. Index will become 1. That's mean we are calling from this, and then this always remain 3, and then 1 left we have filled. So with this value we are calling here. So for left we can again fill. So in that case, 1, 2, 3, 4, 5, 6. So this is left and this is left. We can fill. For right, what we could do, 1, 2, 3, 4, 5, 6. So we are taking quite a long time in this dry run, but it will make it clear what actually this is happening. So right we can make, because if you think about this, one left is there, and so a left is surplus, only one, there's no right, so we can fill right. So with the rule we could fill right here, right? And then again here in left we will call, now we are calling for this indexes. So for left we can again fill left, this is left, this
Sir,
is
for
right.
right, the index value would be?
For this you can see index value will become 2, because we are here 0, 1, 2, 2,
So,
this is 3, and this is basically 2, right? And when we first always try for the left call, so the when again have this left call, so left, left, and left. So after this it will become this, and
so
now
for right, it would index minus left count would be 0 in the
which
second step.
in second, let's me take the color. So this first call is there in this left, so this is actually not executed. I return it first. Let's go how actual execution will happen. First we will go to the left branch, come here, then we'll go to the left branch, just ignore that like that right now, and then again for the left branch. So now this is our status. Now again with the left branch, now this is our status as per our code is written,
Yes.
right? So let's go to as per our codes, let's go by this, and then we have a 3, and then 3, and then this 3 left. Then again it will, now we are calling from this value point, then again our left branch. So what will happen in left branch, so there is, now we will check it should be less than n, so it's not less than n, so there is nothing in our left branch, so it got cut. So then we'll take right branch, so we will assign one right, suppose it's left, 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 and then right. Okay, and then so this value will become, so 3 left, sorry, index, next time it will calling from fourth index. So first one is fourth index, and a total value is 3, and actually total 3 have been created. So this is the way it will call, and now it is calling from this value. So this again left branch is got cut because there is no left available. So only the left branch get, and this right branch is there. So this right branch we will put right here. So left, 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 and right, and then right. So in this case, it's like next one when we are calling it, it's like 5, 3, and 3 left, right? So this again, it will go this way. So it is left is again get cut, and this is right branch. So right, left, 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 right, right, right. So we will fill this. So it will become, now it will calling for next one, it will call it from 6 and 3 and then 3. So now this is actually happen this, and this point it is calling the next call. So what will happen in our code, so in top, whenever if the index is 2n less than, so we will print it and return 1. So what will happen, we will print this selection, so this selection will get printed. So this is one selection, and what will happen, we return 1, so this value will return 1. uh, that value, sorry, this value actually we think about, this value will return 1. So what we will do, we will select count increase by 1, and this is not in this branch is not increased, so there is 1 plus 1 count is only 1. So this value will return here, the value, the right branch which is returning here, which returning here 1. It's saying if we select R here, then only one valid we could generate. And same way this branch is not on, so it will return here, and then it will return, this side is 0 because it's not any selection, so this will again return 1. So it's saying whenever we have a left, 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 then one right, and after this we are going for selection, and then we will actually get select only one valid. And then again here is no branches, no branch here, and this is given 1, so 1 plus 1 here, so it will also return 1 here. So it is saying when once we put 3 left, then after this if we send selection, so whatever we fill after, we can generate only one valid selection. So this is the left of this, so left will increase 1 count here. Now go for the right, so in that case we will select right here, so it will be, so so it will just taking time initially, and then it will become clear how case is generated, then we can move on quickly for next questions. uh, it is the left, left, and left, and then we are generating here right, right. So and then it will call for this point next. So whenever we are calling for this point, it is like this is 0 1 2 3 4. So next point it will be we call for 4 3, and 3 is no need to write again and again, we know it's fixed 3. So just 4, and how many left we have filled 3. So this point it will again, because you already filled 3. So just a sec, 3 sorry, okay, just a sec, the little mistake is that this is a right selection, and before that only 2 is selected. So we here we are selecting right, so this we have selected right here. Now that's why we are calling from 3. So here next call will be for this actually, rather than this. So 3 and 2 is there. So now we will have a both of these calls. So here in this, so this is for left call and right call.
Sir,
Left.
index is where we have to put the next bracket, or where the
Yes.
previous one has been put already.
Next one we will put.
Okay.
So here we'll see that's an index, whatever is the index, that one we are using to fill.
Okay.
Right. So that way it will actually fill. So if we go to next, now we will do a little quickly. So this will be then left, and then one right was already there. One right is already there, and then it will put a left here. And this right will generate left, left, right, right, and these two empty. So in that case, we have two left, then right, and then left. So again, in this case, when we'll go left is missing, we all three we have used. So only right will be there. So it will be this left, left, right, and then left, and then right. So in that case, we reach here, and then again left is not there, then only right. So left, left, then right, then left, then right, and then right. So this will case will be generated, and then we'll call for this. It will like a valid selection. So when it is a valid selection, we just print this. And the same way it will return this one. So it will 1 plus 1. It will again return here. That's one value. This way 1. If after this condition we reach here, we can generate it only one case. And same way here, when we selected this right, this and after that we can have again two branches. So one is left, it is, and then left, and then the right one is get cancelled because we cannot generate it here. So after we have generated this, and then left branches get cancelled, and only the right branch is there. Left, left, right, right, and then left, and then left. So here we will be generated, and then we will call for this. So this will say this is finally generated, so we'll print that also. So this is the another case, and it will return 1 for here. So this will for 1 and side 0, and this will again return the 1. So in that case, if we go there, so 1 and plus 1 2. So it is saying this side. After this, suppose you have taken the right here, and then after that you could also generate two cases. Just a sec. What is when this branch right is there? Okay. Okay. After right you take left. Okay, then you can generate one. Okay, fine. If you take right here, okay, then okay, and then if you take left you can generate one. Okay, let's see what's we are doing missing here. After three left we can generate one case. If we generate right here, okay, okay, right, one right, okay, and after you generate one right and we take one left, so then left one left, you could generate two right only, and that is fine. Okay, but after this if you generate take a right, that you become this, so do this and one case you will generate. Okay, so what are the missing cases? So one case we have generated this two right, this one, and this is one, this we have generated this. So we have generated only three. Let's see where we are missing the cases. Can you find out where we are missing? Okay, got that. Where we have generated, right, okay. This branch, we have not gone through this branch. This branch is still pending. So after we left and when rewrite, so what we'll do, because here is all the valid ways available. So if we move this branch, so it's have both valid cases, left and right. So left is this, and then left, and right is this. Right branch is not there, so this is there. And then now we could make one left also and one right also. So here it will split into two, and both will generate one case. So here, or it will here. So in that case, these two image same. If we'll follow this branch, so only case it will generate will be this. If you follow this branch, only case it will generate this. So that will be generated one this and one this. So same way it will return one and one when we count it. So this branch will generate here two values, and same way it will return two values. So it will generate here three. So left side will generate 3 and left side right, so it will generate 5. So that way we'll get the return 5. So all 5 we have generated. One is this one, and second one we have generated this one. Third one we have generated this. All should be different because the arrangement or left and right is generated different, and this one and this one. So that way we will generate all 5 cases. So this try run is little bit uh, longer for this, but now you understand how we are generated the case and counting the values, right? So this is the cases. So count is run simple. So whenever suppose you have to generate the count for all the value, just keep on counting how much we can increase the valid case or whatever total cases we are generating if we are selecting this value. And for if you are printing value, just reach for the final selection, and this is the selection, and just print that selection and just return. If you're not counting that, you can just simply return, just print those values. So is it clear how we are actually generating the valid parenthesis?
Yes, sir.
Okay, so this is the general way we will actually generate all the possible selection. Let's to a little different question to which usually use recursion just to generate these cases. Just a sec. Suppose you have let's example take a grid as self, or Suppose some point is crossed, another value suppose is written 1 2 3 4 5 6 7 8 9. For simplicity I'm written it like that. Let's leave it 19 20 21. So here is like a robot kind of thing is standing there. So it is something like this grid. This could be something. So here one robot is standing here. So this point is there which robot cannot go. Otherwise robot can move freely in all four direction. Left, right, sorry, is up, is down, is left and right. So initially suppose this is only, and it can take k step. So it could be like you have to print all the valid case step it could take by using following this rule. It cannot go outside the grid. You have to just print all the possible case. Other cases could be like rather than this value, this will be like some kind of coins or something. So it could follow this rule and take only case step in any direction. And then you have to tell how many maximum coins it could collect. Let's first take its only simple one to generate all the possible. So in case of a step, we can explain a step in this values initially. Suppose take initially is go this direction. Suppose k is only 4, then take this direction, then this direction, then this direction. So it's like 19 24. It's like let's change its value. Suppose so for that we just make it different. So let's make it another value. So it's not to be in this order. So it's 19 41 24 28. It's like this. So that's way you can explain one path. So it could be another way, but it's like a basically indexes, different indexes of this grid. So suppose rule is that in taking k path, it cannot take the same position again. So it cannot like go and come back again, or it's like come and come back again. So always have to be different position in this path of k path. So you, what you have to do, you have to generate all the values, and whenever your path of k is complete, you print the selection. So how you will do that? So initially position is given ij. So same way we have done before, we have to have like suppose this is all paths, and we are just printing paths simply, and this is our grid. Suppose if for simplicity take it integer grid, and all the negative values considered is as block. So it is grid. Initially its position is given I and j. So same way we are saving. So suppose we have a selection, and again we can take only k path. So suppose we have a we should not go outside of this. We have a row size and column size, and we have integer k. So because we are filling this selection, we know up to how many selection we have taken. So for that we can take index. Index will tell that we have filled that many values, so that many steps we have taken, and right now we will fill this one. So if index is 3, that means we are filling the fourth step of this. So this is the way. So you tell me now ki how you handle. So first thing, it will not follow the grid. First thing is it has completed all the valid. So how we check that it have taken all k steps correctly, and then you have to print that selection. So what is the condition?
Index less than k.
Yeah, as long as index is less than k itself meant complete selection has not been done. So it has taken less than k steps. So whenever index keep increasing, become k or greater than. So if index greater than equal to, so it will not go more than k, but there's no harm. So in that case, we will just print selection, print path, whatever. This is our method. Can write it anyway. So it will take selection, and in case, so this case values will print, right? So this is the way when it will complete it. Otherwise, what is the condition that it will not fall off the grid? So either you could check whenever you are taking up, down, left, right path, or you can take the path, because in that you are not doing anything counting. You can take the path whenever you have taken the wrong, you just return, don't do anything. So this is like if you are calling outside of the grid, if this I is less than 0 or j is less than 0, because you are calling in all four directions, so you could be get out from any direction, or I is less than or equal to row size, or j is less than or equal to column size. So these are all cases whenever you are calling, and this hurdle also. So because you cannot reach the hurdle, or uh, this is grid grid I j. Suppose we are representing grid by negative values. It could be interview will tell you how to handle. Know that this is hurdle. So it could be any other character or something, or any special value. So like 999 something. So in that case, if that value is less than 0, we are considering that this is a hurdle. So if all these cases there, then we have taken a wrong path. So just return, simply return. Here actually we are not calculating that how many valid steps we are taking, or how many total case steps. So we are simply returning, we are not doing. So in that case, this is actually void. When we will actually find out the maximum coins or something, then we will change that. So in that case, up to, if you reach up to this, that's mean now you have reached a point which is actually valid. So in that case, what we will do, now we have a 4 option, either left, up, top, or down. So this is written, I'm writing for 1, and all 4 it will be the same. So this is suppose take up. So what we will do, we will in our selection, we can have if also. So because we cannot take a step which already been taken, so suppose we can write a method if valid. So it just only for check that we are, this step has not already been taken, other we are taking it. So is valid, we can entire thing can go in this is valid also, or we could make it separate. Suppose we make it separate because rule interview tells later that rule you cannot take the same point again in the same path. So is valid, in that case we are giving the same which we are trying to take. So in that case we have a selection, or we are passing which point we are taking. So it's up, so it will be I minus 1 and j, like this way we can take. So in this selection array, either you could take the actual values of it, this value, or you can just simply have how compiler read this indexes. So in selection, either you could suppose we'll that thing, if it is valid, it says true, so we will select CTI1 selection, and this is for index. Yes. So which one value we are taking, I minus 1 or j? This is our new value. So how compiler actually find out?
Sir, one thing, selection is an array, right?
Yeah, selection is an array. We are assuming we will keep these value in this, right?
Okay. No, actually in that method signature, I think it's written as integer. So
yeah, it's integer. So integer array. Okay. Selection is integer array. Okay. So if in interview tell that all these value are unique, so in that case you can simply write this value and check whenever you are checking is valid, you can check this value from using the grid value. So if interviewer say that this value could be same, so this is not like all same value, so you have to actually write which particular position you are taking. So in this selection you are actually write the position in terms of I or j. Either you can take an array of selection of which have two rows, or you can simply club the I and j into a single integer. So suppose you are in this position, suppose this position. So your compiler do not take two positions, it take only one position based on in terms of row size and column size. Do you know what is that thing? So for every, it will generate a unique position. So suppose this is row is I and column is j. कुछ ज़्यादा fancy हो गया ये. तो compilers के लिए क्या generate करता है? A single integer. How it reach to this particular value? By using its row and column. So it's not important, there's other way around, but it's better if you know. It's just what compiler do, it's I into column size plus j. So this will always generate a unique value for everything, because we know it will, this columns, this value, suppose this value, it will multiply all the previous row wise column size, and then this way. So it will generate linearly a value for 1 2 3 4 5 6 from left to right this way. And it's actually multiply that value by what is the size of every block, and then you find out that particular memory address. But this value is always unique, so that is important. So this will help in two way. Whenever you want to use hash to represent a particular position in 2D array, so you can say make this as a key of the hash. So it's better if you know that. So supposing single selection, you can also do that. So if it is selection, so in that case, you if you want to store that value only, so what we will do in that case, we will store that value is I minus 1 is the row, right? So I minus 1 multiply by column size plus j. So it will always generate a unique value. In that case, no matter, you can always find this value again. So how you find, if you have this value, you can suppose this is x. So out of x, how you could find I or j? So simple. First you take the modulus. You can say how many remainder is from the x. So x, suppose this is x, a column size. This will give you j, and then x divided by column size. This will give you I. So this way you can actually get both I and j. So that is a small details, not very important, but it's become important whenever you are trying to make a single key out of row and column, and especially become the case when you want to save that in hash, because in hash you can save in only single key. Okay, whatever it is, we save this in this way also, because we want to improve our complexity. So we in this is valid. So in this this selection values, we will use a hash so that we could do it faster way. Otherwise in here we will do it linearly by one. We'll check using the one by one if this any values is created by this. So either we have selection, and then what we'll do the same all paths. All paths, all paths, what we have a grid, everything remains same. Only thing will change, this I become I minus 1 and j, and index will become index minus 1. Selection, row size, column size, k index. So I'm changing index first here. So index will become index plus 1. Everything will remain same, row size, column size, or k, or selection. You cannot change that sequence in actual code. I'm just change here. So you have to always remain the same sequence, whatever you have defined by this. So just to explain this, so this way you have taken the up, same way you have taken down and all everything. So it will keep on generating all the valid ways. Whenever it will generate a full selection which is valid, it will just print that thing, right? So this way we actually keep on generating. So first thing is, if suppose we are generating this way and we are taking k path, and this is a quite a big grid, and there is usually we are not taking the same position which we have already taken in the path, then what will be the roughly what is the time complexity? So how many branches are there? One is for up, one is for down, one is for left, and one is for right. So so you tell me how many branches is there and how many level is there? So how many branches there in this recursion? Every time how much a one recursion is splitting in how many different recursions?
4 different.
Yeah, 4 different, because if you are here you can move in, suppose you are here, you can move in 4 direction. So but if you follow the simple rule that if you cannot use the same point which you have already taken, so that's mean if you are here, you are coming from this side, you cannot go this side again. So that's mean last step was down, then next was not up. If last was left, then next cannot right. So effectively branch will become 3, right?
Yes.
So if branch is 3, and now level, how many level will be there? So how long our path could be?
M plus n.
So actually no, we have given that only k length path. So you have to print all the paths which are k length. So our level is k. So time complexity is O 3 to the power k, roughly this, and this is good enough to tell in interview. And what is space complexity? So in a space complexity, we are using this selection array to keep selection, intermediate selection, and also the recursion will take time. So this selection length is also k, and recursion level is also k. So it's k plus k remain k. Okay. Because the input grid we have given, it is a part of input, so we do not consider that as we are taking extra space. So this is time and space complexity. Suppose interviewer change it a little and say that there are these coins are there, and coins could be all positive, negative. So first thing, before that, let's just move before, because our time complexity had little problem. So look at this. So this is O1 O1, but this step is not O1. How much time it will take? This is our selection array which is so far we have selected, and this is the new index we are selecting, and we are checking if this is a valid one. We have not selected it so far. It is like we are just taking this, and then with this, then this, and then again we are try to take this. We have already taken this or not. So how much time it will take?
If it's a hash map, then O of 1.
Yeah, so if it is we are checking only again selection, then it will take okay time, because the length of the selection array, because we are checking one by one. So the effective our cost is k into 3 ki power k. So first thing, you have to reduce this code because this is reducible. So as someone suggested, rather than checking this array, if you keeping this value in the hash, so if you keeping this value into hash, then it is easy to check. So if you are, suppose you have a hash also, suppose you have a my hash here, and in this hash you are adding, so you are you just adding this value, whatever you are, this value is there. So I minus 1 multiply column size plus j, this is key, and if this you value kuch add just one add. So you are adding in this hash. So rather than inside this selection, you just use in the hash itself, my hash. So my hash. So what will my hash will get? It do a get call instead of this get call, and based on this key and check if it is there or not. So this will now will convert it into O1. So now it will get converted into O1. So this will again, no, you don't need it. So but important thing is this, which usually students do the mistakes, which is that I told you, whenever you are using recursion to do some selection, so you always have to undo the selection. So what is missing in our code right now?
We are not deleting the value from the
Yeah,
hash.
so whenever our recursion is returning at this point, so we have to remove this value from the hash. So here this is a must, because hash is not like an array where we override. So here we have to delete same value whatever we are adding. And then we can select next, because now we have already deleted this. Now then we select the next step. So this is up, next, down. So up information from hash is gone. So now this is, it is good so far. So it will take time complexity to the power k, and now we take the space in selection, recursion, and then hash. But all three, if you think about, so all three will be uh, this is our selection array, okay, then our recursion stack, okay, and then hash, okay. So all three is okay. So again became k only. So okay, so it's remain the same because in the same order we are using that. So this is the way we will generate all the path and print that. If interviewer change this values, like this is plus and negative value, and every value represent a coin, right? So coin values, so it will positive, negative. Hurdles you are already handling. So in that case, hurdle, suppose you have given hurdle is a special number, so only one some number is hurdles. If it this integer array, if it is more than, so if this is equal to, like hurdle is a special number 9999, all these are hurdles, all other values are, or usual negative values are available. So in that case you will return if this is hurdle. So all other cases is a positive value or negative value. So you have to, rather than print all the values, you have to find out the path, k length path, which follow, by following this rule you can collect the maximum coins. So what you will change, so first it will return a value. So integer, you have to maximize. So you have to use a maximum method where you will use max.
Max of all four directions.
Okay, max of all four directions. So actually what it will do, suppose you are going, and here let's go here. So what you will do, um, when you will complete this selection, here you are completing selection. So here what you will do, so when you complete it, so in that case whatever is uh, the sum is actually is making, you just return that sum. So before that suppose it's have taken 4 path, so every path will return its sum. So whatever sum it is making, it will select the maximum sum out of these. So in that cases you always select returning which is the currently maximum. So it is like you are a particular point in this grid, you are here. Suppose after that you take 4 path and both are like valid, so out will return their sum, this, and you will select a maximum of these things. So this thing, and if after that it's already taking some values, two values all, and then everyone is returning out of these two the maximum, and then out of these four it will returning, so automatically the maximum will be returned. So in that case, even though we cannot do some sort of memorization, because the things could be many more, but what we'll do, every value, so here we can just return we can return get sum. It's simple, we can get sum here itself, get sum of selection. It will do nothing but select sum all the values and return it sum. So it will simply return the sum, whatever value we have selected so far, nothing else. So in that case, here whatever value is there, so out of all four possible values, we will just return sum. So in that case, we are actually already taking this value. If this it is not valid, suppose we have taken a selection, it is not valid selection, what we will return here? That mean out of these four, we have taken selection, but we have called outside the grid, something like, or we have called the hurdle. So what we will should return if we are maximizing?
Min value.
Yeah, min value. So this is the simple rule. So how we handle if we are maximizing min value, if we are minimizing the max value. So that case we will return min. So here what we'll do, so in that case either we will take its value, or we can have a simply, we have to return like a max variable, max v, or initially it's give it some min value. So whenever we give its min value, whenever it's get any other value, it's maximize. So how to handle this? Max value will become max of either previous max value or whatever the new value it will return us. Yes. So in that case, it will call for the up. If up value is giving its any other better value, so it will update the max value. Then same way we'll call for down, left, and right. So effectively, it will take the max value of all four. You can take the four variable and then take the variable. It's the same thing. So, but in this case, our recursion will take the same time, because there is no single simple way in which you can save, because you cannot save here like this value, if I reach this value, it will always give the same. So there is way to save, but we are not discussing it in DP thing. We will discuss how effectively even in this case we could save. So in that case, we are taking this same time, same space, but from all the valid paths, we are taking returning the maximum in we could get in all the valid paths of this, when this robot can move around in this grid. So is it clear now how we will use recursion to generate different kind of selection?
Yes, sir.
Okay, sure, because next problem will be a real tough selection using recursion. So okay, let's see how we understand, because this is a simple 2D grid. You guys know Sudoku?
Yes, sir.
1 to 9. So let's write a program with a brute force to fill the Sudokus. So I'm making a small one and then run fit the actual one. Suppose this is small. That is small will not help. Okay, let's write a full Sudoku. So you have a given a Sudoku. So some values are empty and some are filled. The rule of Sudoku is that you can fill value from 1 to 9. It have 9 rows, 9 column. 1, 2, 3, 4, 5, 6, 7, 8, and then 9. Same way 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so it's 9 into 9 grid. So rule is that whenever you finally fill it, so all rows and all column and all the grid, this is also get divided into 9 grid. It's like this. 9 grid, 9 3 into 3 grid. This is divided this. So all row should have 1 to 9. All row should have 1 to 9. Same way, all column, all rows 1 to 9, and all grid. Suppose this is one grid, so there's 9 different grid. Every grid, all values should be 1 to 9. So all 3 into 3 grid 1 to 9. So not any grid possible, but only these 9 grid. So you can say this first, second, third, fourth, fifth, six. So some value will be filled initially. Let's suppose it's written 2 here, 9 here, 6 here, 4 here. But I'm writing randomly, but it would be based on some value, so that you could fill all other grid for this value. 4, like 8. Suppose this is this fill. Now you have to fill the entire this Sudoku by using recursion. That's mean trying all possible values. So how you do that? Okay, before we write the actual recursion, one thing which is important in Sudoku. Suppose at any point, I am want to fill this I and this J as some value, like anything like 4 or 5, anything. I want to check. So I want to check if this value is valid. So valid mean if I'm putting in I and J, then this I row, the entire I, this I row, suppose we are putting some value here. So this entire I row do not have this value, whatever I am putting, and this J column, which is this column, this entire J column do not have this value. That is clear, because I and J row we can directly go from this grid. This is Sudoku grid. But other thing is, I want to find out in which 3 into 3 grid it is lying. So in which 3 into 3 grid it is lying, no other value will be the same value. So this is clear. To check the row, check the column. How to check into 3 into 3 grid? Can anyone suggest how to check 3 into 3 grid that other values are not the same based on I and J? So let's me explain again. The entire grid is 9 into 9. So entire grid row is from 0 to 8. These are rows, and column 0 to 8. So but inside this 8 group, there is 9 3 into 3 grid. So first grid is from, suppose write 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. So this first grid, if I'm thinking this one, so this is from 0 row to first row 0, and column, this boundary, if I'm saying it's boundary, it is from 0 row and 2 row, and 0 column, 2 column. Next one, if I assign them the numbers of this grid. So this is, I am calling, this is first grid, this is second grid, third grid, fourth, fifth, sixth, seventh, eighth, ninth. So there are 9 grid. So first, whenever you have I and J, you have to find out it's falling into which grid. And then in this grid, suppose you have this grid. So we know this, this dimension is starting from third row and fifth row, and column is 6 to 8. So in that case, if we have given I and J, so how you will check what in whatever grid it's falling, how to check that no other value is the same which you are trying to fill? So that if one problem is there.
We can divide I and J by 3, so we'll know to which grid to fall into, and then run a loop for 3 values, and loop over that grid and check whether that value exists or not.
Okay, so whatever you told, just let me make it clear. So actually told, so whenever you have a I and J, so if you find out the first position of when your grid is starting, so it is starting from 0, 0. So you will immediately know its size, because you can start the loop of 3 and 3 row and 3 column, you will have the entire. So if you, for any grid, suppose you are here, you could find the starting, or just you can say top left, you can find the top left value of any grid. Suppose you are here, so you know that this row and this one, so 3, you can just make a loop of running 3 row and 3 column, you can find all the value. So point is, whatever point is your is, you can find at the top left position, then you can find the entire grid. So how to find the top and position? So it is, if you think about, if your value is this in between 0 and 2, so top mass position is 0. Now if we in this position, so row is from 0 to 2, so this position is row will be given 0, but column position is giving 1, and this column position is become 2, 0 and 2. So as he said, this finding this thing is simple. So you know, this is divided into 3 grid. So just divide I by 3, it will give top left row, and j divided by 3, it will give top left column. So you check it for anything. Suppose this is let's this, so this is 7, this is 7 row, and basically 5th column. So if you divide by 7, it will give 2, sorry, this is actually divided by this is only give which grid it is falling. So in terms of rows, because this is first row grid, second row grid, third row grid, and so it is like which row grid is falling, and then you know the grid side is this, like the compiler will find out if it is no one item is made of this thing, so it will find out how many is there. So in that case, you will find out in which row grid it is and multiply by the size of the grid. So it is little tricky, which we are using. Let multiply by 3 j, because we know that grid size is multiplied by 3. So this will give you accurate coordinate. What is trying to do, so whatever is your row is, so row is 7, so it will try to find out of 3, this row grid have 3 rows, one row, second row, third row. So which grid row is this? So grid row is when I divide by 3, that's a 2. So it's grid row is 0, 1 and 2, and column this same way grid column grid is 0, 1 and 2. So we'll try to find out. In that case, it's like the compiler find if size of one block is this. So in that case, when 7 we divide by 2, so it give 2. That means it's find out in third row grid, and that is will 5, and divide by 5 by 3. So this value will give 1. That means it's one of one column grid. Then what will do to find out the first value? So whatever grid before that, multiply by 3, so it will give the first location when the column will start. Same way, and the row will start. So in that case, it's calling in the second grid. So before that, it's 2, it is getting into 2. So 2 into multiply by 3, that's mean this is 6, this position. Same way, column is in this case, column is getting 1 multiplied by 3, this. So this is the shorthand to find out the leftmost of any grid, topmost, top left of on any grid, which is no, if you are provided I into j. So just think about it. It will take a little time how you find out this, because whenever you are filling Sudoku, it converts into 2 problems. One problem is how to check in which small grid you are lying and check its elements, and another is write the recursion. So this is almost as tough as writing the recursion. So this is the rule to find out the your topmost whichever grid you are lying, and is top left, and then you have just have to for loop of 3 and 3 size to check all values. So is just getting clear how we are getting this rule, or we'll just discuss it a little more? So it's look like
I think we should discuss once more, sir.
okay. So it's little confusing. Let's check one value. So it is like what I'm saying, I have divided into 3 into 3 block. So in terms of grid, now I am defining the grid row. So this is grid row. So grid row 0, grid row 1, small. I'm talking about only 3 into 3 grid, and grid row 2, and the grid column 0, grid column 1, and grid column 2. Right. So what this row into divide by 3, what will do? It will give us the grid, whatever grid we are lying, the grid column actually. So it will give us the grid row and grid column, this thing. So when we say I equal to 3, it will give us grid row, and j equal to 3 equal to grid column. So let's pick any values. Suppose we are here. So 5 and 7. So divide 5 by 3 is give us a value of 1. So it's saying the grid row is this, and it say what this value is 7. So 7 by 3, it's giving 2. So that's mean grid column is this. So that's mean this grid row and this grid column, we will go and we will find a value. So this is our grid. So now we are able to identify which grid is this by using I and j. So far it is clear how to find grid row and grid column.
Yes, sir.
Yes.
Okay, now we will we have a grid row and grid column. We just have to find out grid first topmost elements value in terms of our actual 9 into 9, right? So once we have find out, suppose this 5 and 7, we find out our grid row is 1. This is 1 into 2, this. So this is in terms of grid if one element is of this size, but actually in that case our actual row, this grid row is of 3 row, equal to 3 row, and grid column is equal to 3 column. So what we'll do, how many previous row have been before that. So whatever is the row, we will multiply by that by 3. So 1 multiply by 3 and 2 multiply by 3 by 6. So it will actually be get converted. So how many whatever is the row, how many row will be before that. So 1 into 3. So that's saying how many row will be before that. So 1 2 3. So how, so we will actually effectively will be fourth row. So if it is the 100, so we will row will be fixed this. And then for column is 2. So 2 into multiply 3 6. So 6 column will be before that, before this grid actually. So 1 to 6, and then we move. So we are fixing our column or basically row. So now this will be our topmost. So what we are doing, this is giving whatever grid row and grid column. So because every row grid row and grid column size is 3, so by multiplying by 3 we will find out how many rows, actual rows are before this when this grid is starting, and how many actual column is before that before our grid is starting. So that will give us the top first position of the grid. So that thing is done by multiplying by 3. So is it clear now? So how we are trying to do that? So just think about it. When you will do it yourself and make this grid and try to find out for everything, you will get make sense how this thing is actually working. So this is like a sub problem of solving this problem. When you solve this problem, then you only think about writing recursion. So this is the rule. So whenever you have an ij and you have to find out the stop grid position, so you will multiply I divide by 3. It will give you grid row, and to convert it, and you have to grid row, but you have to find the first topmost row of this grid. So just multiply by 3, and then j by 3 will give you grid column, and you want to find the first column of this grid, just multiply by 3. So we are getting it because we are starting row and column are starting from 0. That's why we are getting it the correct one. Otherwise in actual time you can say if grid row is 2, so that's mean 2 into 3 row is before it, and same way if grid column is 1, that means 3 column is before it. But row and column are starting from 0, so that is our answer. So in which row and column it will be there. So when we have this top row and top column, so if you check, so if you have method check a small grid. So this is our main Sudoku. So integer Sudoku क्या होता है सिर्फ को सपोज आप इसे लिख देता हूँ, something is different, and we have given integer I, integer j, and the value we want to put, suppose this value is integer we want to put it here. So what we will do, by using same values, we will find out integer top left row, it will be I divided by 3, this, and then multiply by 3. And same way, top left column, j divided by 3, and then multiply by 3. So after that we have to just make a loop for I equal to 0. So is the first one, I is less than 3 when I plus plus. This is for row, for j equal to 0, j is less than 3, and j plus plus. So we have not filled our value, so we will check all values. So if this is Sudoku, this is I, oh sorry, we have to add this value. So even we could here do it self also, rather than, I think it's fine if Sudoku. So this is our, this grid we are starting, and this is add row we are adding it. So it is top left right, and we are using I plus I. This is become our row. So initially when I 0, that's the same row, and next time it will give top left column plus j is up for our column. So this will become our effective value inside this small grid. If this equal to a value whatever we are trying to save, we will just immediately return false. Or this is, let's suppose, a Boolean one. If we run this entire for loop and we have not written any point, that's mean everything is good so far. So return true. So this is our code. Whenever we have a point, suppose this is our point, so we'll start from here, and this in this we will check in this row, then in this and this 3. If none of the values, so we want to put 7 here, none of the already filling value is 7, then we will fill it. So this is the way we will check. So row check and column check is simple, and a small grid check is this. So now we have written the check. Now we will actually try to fill the Sudoku. So what happened in Sudoku, some value have been already been filled, like 2, 8, 7, and all other value we will fill. So whatever value is initially filled, we will not change that values. We will fill all of the other values. So roughly how many values we need to fill? How many values are there in? How many total values are there?
81.
81, yes. And for fill every value, how many values will be there? Which are the possible candidate?
8.
Actually 9, 1 to 9, right? So what will be the time complexity? How many levels will be, recursion level will be there?
81 total values, and for every cell we have to check 9 values.
Right. So how many branches are there for recursion? So when we are selecting, so how many different selection we are available, all become our branches, right?
9 branches.
So branch is 9. And how many level will there, because we do not know how many value will be given to us. So it may be suppose 10, 12 values, but let's assume all values are not given. So whenever value is not given, this branch will get split. So in worst case, like 81, maybe this like all more or less empty. There are many solution of this. So our level will be 81. So there will, it will be little less, some like 81 minus L. Suppose L value is already given, this could be 10, 12 or so these will be our level. So roughly it will be We don't know how many L will be, so 9 to the power 81. So this is our worst case complexity. It's like actual, so whenever value is given, we will not change that value, that will fix forever. So 81 minus L. So this is our time complexity. So the same way we'll try to fill that. This, let's write it somewhere else so that we have a space. Okay, so this is our code. Fill Sudoku. So initially we have a grid, which let's call it grid, and in that grid itself we will fill. So how we will identify a single value? By location I and j. So we want to fill in this integer I, integer j, that is column. 9 we know size, so no need to send size. And then anything else, the current selection we will keep in this grid itself. So I think it's fine. That's all we need. Okay, so how we will generate the new values? When will this will happen? When all will be finished. So this, you need to select in which order we want to fill. Let's go to our grid. Where is our grid gone? That's why you have to make it here. So in that case, you have to select which way. So we will, usual way is like fill row by row. So every row fill from left to right, and then next row, then next row, then next row, from left to right for the column. So same way we will fill. So that's way whenever we will fill the last, where is our code? Yeah, Fill Sudoku. So we know that we have filled the entire, that's mean our row will become 9. So this row, we could write it for generic Sudoku n into n. Let's write it for generic Sudoku and pass n value equal to 9. So then it will become for any generic Sudoku integer n. So in our case n is 9. So actually what we are doing, we are filling row by row. So whenever if your row is increased, like I become less than or equal to n, so that's mean you have filled all the rows. So that means you have filled entire Sudoku. So just we will print it. So in that case, print, this is our method, print Sudoku, and we will pass it our grid and value n. So this is when we calculated it. Otherwise what we will do, we are landing at this point I and j. It could happen that this already been filled. So if this value is already been filled, what we will do, so initially we have to fill all the values of 1 to 9, right? So by default what we will do, say in this grid, all the value which are not filled we will fill by 0. If it is given, then it's good. Otherwise initially what we'll do, all non filled value will make them 0, so that we know that these values are not filled. So if that value is not 0, which we have already landed, then that's mean it's already been filled, we cannot change it. So it is like if, so if grid value I and j, in which we are trying to fill the new value, maybe the first value already filled, it's you can say not equal to 0. अगर ये not equal to 0 है already, then we don't fill anything. So what we'll do, we have to go to the next values. So next value, that will in row I, we will go to the j plus 1, right? So we will fill the next value. So we will call the fill Sudoku for the next value. But problem is that it could be like you are filling the last value of the row. So it, suppose this is the grid. So if you are here and you are, there's no next value, then you have to fill this value, right? So in that case you have to find the next value. So j, so it is like if just make a simple if j, this is already, you can say, this is already been like 8, so 9, so there you cannot move to 9. So if j plus 1 equal to n, so that's mean if it is it become equal to n, so in that case what you will make, you will change the row. So in that case you will call fill Sudoku grid. You will increase the row, that means row will increase plus 1 and column remain 0, become 0, because that's mean you will the last one, now you will fill the first one. It could happen this will also fill, then it will go again, and that's not a problem. So and then all stick remain same. So in this case you will call this. Otherwise, let's fill here. And if this else is for this if. So if this is not n, so not equal to n, that means it is less than, or you can say, you can return opposite also, less than n this valid. So I am assuming it will never going the value more than that, so it's always less than n. So in that case fill Sudoku grid, that's mean the next value of the same row. So row is I, and this will become j plus 1 plus n. So this is the case in which the whatever value we are actually entering, that was already filled, so we do not touch it, we have not touching this value, we just call the next value. If that is not the case, so that's mean the value we are coming, it actually 0 values. So what we'll do now, we have a for loop for, and that 4 is I equal to starting from the 1, I is less than or equal to 9, and I plus plus, right? So you this is the value we are trying to fill. So we will check this value, if valid. So if let's make a single method, if valid for okay, if let's make it is valid. So if this is valid, so we are passing its value. So same way we are passing its grid, or in that case I j, and this value, sorry, ij we are already been used, so let make it k. uh, so k is less than n, k is, so k is our value. So that will, so it will this will have a 3 separate method, row check, column check, and the method we have just written. If this is true, so that's mean we can that value. So in that what we'll do, we will call the fill Sudoku. So again, fill Sudoku is like the same way we have to check it's the last value or not. So we could also either we have to check here also we could find out that value before what will be the next row and next column, and pass the same value here and here also. We have not written it, so I'm doing the same thing here. So the same code it will be here. So same way, because it could be the last value. So if that's where j plus 1 is equal to n, so we will fill Sudoku and same. Before filling, we will actually put this value. So in this grid, we will put it before that. So do not need to write it because we are already writing twice. So that you could write avoid by using variable. So in this grid, I and j, because it's saying is valid, we have put this value k. Right. So in this, and that just the fill Sudoku. So it's grid this row plus 1 0 and k, and same way as else, just to write it's again Sudoku grid. In that case, it's a usual case, row remains same, and that will become j plus 1 and k, right? So it will, the else is here. So after this is when it says it's valid, right? So if this is valid, we will fill this with variable k and just call for the next row. It will call, if it is valid, it will print that, and then again it will come, it will the next. So here actually every recursion, whenever we finish a recursion, what we have to do, whenever this recursion is got finished here, we have to override whatever selection we have done, we have to undo that selection. But in that case, actually we are overriding the same position I and j, so we don't need to actually explicitly undo that, because next one will override. So in first one was 1, next one will be 2, so override that thing, so no need to done. But if you are doing this selection in list or any other value which is not array, so you have to explicitly make to the undo whenever this is written here. So it will try all the 9 values and then it will return. So here important thing is return again. So all this thing we have done because we find this value, this particular value was 0 when we landed, right? So that mean it is not the value which was given in the Sudoku initially, which was not the fixed value. We have tried those value. So to make this thing remain open, so we have to undo that thing. So again we have to give this value grid before returning. That is important part. I j again 0, so that when we back and we say move back and forth and come back again to this value to fill, it will again remain empty and then return. So what this our code is doing, so this code is actually trying to fill all the values from row by row, from left to right. So if it whenever it land a particular value ij, so it will check its value is already been filled. If it already been filled, that's mean it is been filled, but it's given as a value of the for that position. If it is given that value as position, is do not touch that value. So it just calls for the next value, this one, and then and before after that, if that, and let's put here return also, that is a big mistake. So actually we call that, and again we know. So before that, inside this if, it should be written. So what it's doing, if this value is already filled, you are not touching it, just calling for the next value. If this is the last element of the column, that's when you for the next row. If it's the not the last element, that's the next column, this row. When it will return, you will return entire this thing. So because you cannot fill, if it is not go inside this if, then it will go, because inside this if we are returning itself. Then we are trying all the values from 1 to n, and we are checking is valid. Inside this is valid, we will roll all 3 checkers, row check, column check, and then small grid check. If that return true, then we will fill this value grid value, whatever value is k, and then again the same value, this check we are writing 2 times because we have not saved the values for next row and column. So in that case, again if it's the last value of the column for next row and the first 0 column, otherwise the same row next column we are calling this. And when we are returning this, and then again we are trying new value, then new value, all 9 value we will try. And after, before returning, this is the important step, initially we get this value 0, that indicating this is the value open to fill. So we, before returning, we again fill it 0, so that when we come back again doing the recursion, we find this value 0, and then we'll return. So this code will for the entire Sudoku run from left to right one by one, and then actually fill the entire Sudoku. Yes.
So,
Hmm.
sir, I didn't get that undo part. Like, if we have already filled the grid ij with some value, then why do we have to put it back to 0?
Okay. Let's understand with a small grid. Okay, suppose this is the case. Initially, suppose this is 1 to 9, and this value is already been written. Let's suppose 3, and this is 4. These are like fixed values, and this is also 5, right? So what is happen? So this is value to open. So in first time you try 1, so 1 is fine. You started with 1 here, and then you fill the entire grid. Then you come back and try with 2. Then you fill. So let's then this. Let's make another value. Yes. So how we are knowing that this value is already been filled? Suppose this is filled 4. So suppose you are from this. So this is not filled. Suppose you filled 4 here. Then you come here. So you initially first try 1, then try 2, then 3, 4, 5, 5, 5, and all value, print all the value, all 9 values. So now last value you tried, suppose 9, and 9 was fine, and you have not overwritten it, and then you come back. This call was coming from here, right? So in that case, instead of 4 you tried 5 here. So 5 is already there. So then you tried 6. So 6 is fine. So then you come back here, and then you here, and you will check it's already 9 is there, right? But whenever this one value is already been there, you consider that this is the value given initially. You cannot manipulate that. So you do not test that value and come here. But it's not the case. When you try 6 here instead of 4 again, when you come back, you will again have to find this values able. You can manipulate any value from 0 to 9. That's why we are keeping it 0 whenever before returning. When you try all the 9 values, after returning it will make this value 0, so that when it will come back again, so it will actually try to all 9 values again. Now you're getting the point.
Yes, sir.
So it is to differentiate which value is given to us initially, like 5, 3, 4. This value is given initially, so we do not touch them. So whenever we come back, suppose here initially we try some value here 2 and come back it's 3. So we just move it to here. Next time when we return and come back, we again find the same value. So this value non-zero is saying we can't touch that value; it will remain fixed. But all the other values indication is make 0. So whenever we try all those values, all 9 values, and when we return, so we make it 0, so that when we come back again to this point, we find this value 0, because 0 in negating we can manipulate. So these two steps are very important. One thing is that to check this value is already been fixed, so do nothing in that case, just call for the next value and return here. And same way when we try all these values, so we have to keep it return back to the same value, grid 0, and then return. So even
सर
yes.
एक क्वेश्चन कि सपोज हमारा फर्स्ट टाइम में ही पूरा सुडोको भर जाता है, बट हम जो है बार बार उसको ट्राई करते रहेंगे विद नेक्स्ट वैल्यूज.
यस. सो इन दैट केस ये है कि अगर आपको सिर्फ कोई भी एक सॉल्यूशन देना है, दिस ओनली वन सॉल्यूशन, राइट? सो इन दैट केस आप जब यहाँ पे प्रिंट कर रहे हो यहाँ पर, तो यहाँ पर बेसिकली आपको रिटर्न करना है. तो इस वाले केसेस में हमारा ये वॉइड है, तो अगर हम इसे सिर्फ एक बार प्रिंट करना है, ठीक है, तो उस वाले केसेस में हम यहाँ पे रिटर्न करेंगे रिटर्न ट्रू. ठीक है. और इसके बाद क्या होगा, जब भी हम किसी इसको फिल जैसे सुडोकू कॉल करेंगे, तो इसका जो भी रिटर्न आएगा अगर वो ट्रू है तो हम इमीडिएटली रिटर्न कर जाएंगे, आगे कहीं नहीं जाएंगे. इसी तरीके से जैसे यहाँ पर है, हमने यहाँ पे पहला रिटर्न ट्राई किया यहाँ पर, और हम जो रिटर्न आया अगर वो ट्रू आ गया, तो फिर हम कुछ इमीडिएटली ही रिटर्न कर जाएंगे. तो उसके थ्रू क्या होगा, सिर्फ एक सॉल्यूशन प्रिंट होगा और कुछ नहीं होगा. अभी हम वॉइड कर रहे थे तो हम सारे कर रहे थे. अगर हम इसको यहाँ बूलियन कर दें, कोई भी इंडिकेटर जो बता दे कि हमारा एक रिजल्ट प्रिंट हो चुका है, सो वी विल मेक इट बूलियन. सो हमेशा हमारे पास फॉल्स आएगा जब तक कोई भी रिजल्ट प्रिंट नहीं हुआ है. तो अदरवाइज ऐसा हो सकता है आगे जाके कोई केस नहीं मिला, वापस आ गया, तो उस वाले केसेस में हम रिटर्न ट्रू यहाँ पे हम प्रिंट करेंगे. ठीक है. तो जब भी हम करेंगे यहाँ पर, जैसे कहीं पे भी आ गया, जैसे यहाँ पे ही आ गया ट्रू, तो हम यहाँ पे रिटर्न कर जाएंगे, फिर रिटर्न ट्रू. तो उस वाले केसेस में जैसे हमने ये फिल करा, और अगर इसके बाद ये ट्रू आ गया तो हम रिटर्न ट्रू कर देंगे, अगर ये फॉल्स आया तो रिटर्न फॉल्स, जो भी आएगा वो रिटर्न कर देंगे. इसी तरीके से यहाँ पे कॉल करेंगे, तो अगर ये कॉल यहाँ पे कॉल हुआ, अगर ये ट्रू रिटर्न आ गया, तो हम यहाँ पे इमीडिएटली यहीं से रिटर्न कर जाएंगे और कुछ ट्राई नहीं करेंगे. ठीक है. और अगर हमने सारा ट्राई कर लिया और कहीं भी रिटर्न नहीं आया, कहीं रिटर्न नहीं आया, तो यहाँ पे रिटर्न फॉल्स होगा. ये फॉल्स इंडिकेट कर रहा है कि हमने सारी वैल्यू ट्राई कर ली और आगे कॉल भी कर लिया, लेकिन कहीं पे भी कंप्लीट सॉल्यूशन नहीं बना, तो उसके बाद हम यहाँ पे फॉल्स कर देंगे, ताकि पीछे पता हो कि फॉल्स है, वो अगली वैल्यू ट्राई करे. आया समझ में कैसे हैंडल करना है इसे?
यस सर, यस.
ठीक है. तो ये वो तरीका है जिसमें आप सिर्फ एक वैल्यू प्रिंट करोगे, लेकिन जब भी आपसे कॉम्प्लेक्सिटी पूछी जाए, वी डोंट नो कि वो एक वैल्यू कब आएगी. वी ऑलवेज थिंक अबाउट द वर्स्ट केस. तो वर्स्ट केस आपका वही रहेगा 9 टू द पावर 81, और 81 से कम होगा बेस्ड ऑन की कितनी इनिशियल वैल्यू आपकी दे रखी है, और लेवल आपका, और जो स्पेस कॉम्प्लेक्सिटी पूछे अगर इसमें स्पेस कॉम्प्लेक्सिटी, तो आपके जितने लेवल हो सकते हैं, तो वो ये 81. ठीक है. इसमें और कोई स्पेस नहीं लग रहा है, क्योंकि हमने कहीं भी कोई वैल्यू नहीं रखी, विद इन दिस ग्रिड ही हमने अपने सॉल्यूशन रखा हुआ है. ठीक है. तो बहुत सारे कुछ कंपनीज में खासकर जहाँ रिकर्शन के कोड, रिकर्शन सबसे ज्यादा पॉपुलर है सभी क्वेश्चन में, तो इस सुडोकू कोड पूछा जाता है जस्ट टू अंडरस्टैंड कि आप बेसिकली रिकर्शन हैंडल कर सकते हैं कि नहीं कर सकते हैं। तो आपको बेसिकली ये ब्रूट फोर्स वाला कोड ही लिखना होता है, बट यू नीड टू नो कि हाउ टू यूज रिकर्शन टू जनरेट डिफरेंट केसेस। तो सबसे इंपॉर्टेंट चीज इसमें यह है, जब भी आप रिकर्शन केस जनरेट करने के लिए यूज कर रहे हैं टू डू एनी सिलेक्शन, तो वो जो सिलेक्शन है उसको आपको रीडू करना होता है, अनडू करना होता है जब भी आपकी रिकर्शन की कॉल वापस आती है। सिर्फ और सिर्फ एरे के केसेस में आप उसको एक्सप्लिसिटली अवॉइड ना करें, वो अवॉइड कर सकते हैं क्योंकि एरे में जो सिलेक्शन है उसी पॉइंट्स पे वो बेसिकली ओवरराइड हो जाएगा, लेकिन वो ओवरराइड उसी के लिए होगा अगली कॉल के लिए। अगर आपके पास कुछ ऐसा है कि आपने कोई किसी चीज को चेंज किया है और जो सिर्फ आपने रिकर्शन के कॉल पे, तो उसको वापस उसी कॉल पे रखना पड़ेगा। जैसे वाले केस में हमने 0 पे लिया था तभी हमने रिकर्शन से वर्क किया था, तो वापस हमें रिकर्शन से पहले ओवरऑल जब हमारा कॉल उसको वापस 0 करना पड़ेगा। तो ये बेसिक रूल है, यही मिस्टेक यूजुअली होते हैं। आप एरे में या हैश में डाल रहे हैं वैल्यू निकालना भूल जाते हैं, या फिर सिलेक्शन जो लिस्ट में डाल रहे हैं तो आप उसको रिमूव करना भूल जाते हैं, ये कॉमन एरर है। तो अभी इतना ही रखते हैं आज के लिए। हमने रिकर्शन में थोड़ा डीप डाइव किया और खासकर रिकर्शन लर्न किया जिसमें रिकर्शन विल बी यूज टू जनरेट मल्टीपल केसेस। नेक्स्ट क्लासेज में हम रिकर्शन से शुरू करेंगे, बाइनरी ट्री में कैसे रिकर्शन यूज होता है। दैट वाज वन ऑफ द मोस्ट के इंपॉर्टेंट केस ऑफ रिकर्शन और दैट्स व्हाई बाइनरी ट्री बहुत पॉपुलर भी है। तो वो करना शुरू करेंगे। साथ में वो कुछ वैसे रिकर्शन लर्न करेंगे जिसमें पर यूनिट जो सिंगल रिकर्शन की कॉल है उसकी कॉम्प्लेक्सिटी इनपुट पे डिपेंड करती है, इनपुट साइज पे डिपेंड करती है। हर यानी कि हर रिकर्शन की जो कॉल है उसमें जो कॉम्प्लेक्सिटी है वो सेम नहीं होती, बेस्ड ऑन कि वो ट्री में किस हायरार्की में किस लेवल पे आ रहा है। तो जैसे कि मर्ज सॉर्ट है, अब उससे पहले एक बात देख लेना, तो मर्ज सॉर्ट में आप देखोगे तो रिकर्शन की हर कॉल का टाइम सेम नहीं होता, बेस्ड ऑन कि वो कितनी साइज का इनपुट को मर्ज कर रहा है। तो वो करेंगे कि उस केसेस में कॉम्प्लेक्सिटी कैसे निकालते हैं। तो अभी के लिए इतना ही रखते हैं। नेक्स्ट क्लास नेक्स्ट सैटरडे रखते हैं, और आई थिंक सेम टाइम इज फाइन फॉर एवरीवन।
यस सर।
ठीक है, तो मैं अभी ये स्टॉप करता हूँ इसका। तो किसी को कोई और क्वेश्चन तो नहीं है? मैं आज क्या करूँगा, जो ग्रुप बना दूंगा उसमें मैं क्वेश्चंस भेज दूंगा, उसमें आप इजी क्वेश्चन स्टार्ट कर सकते हो, बाकी सारे क्वेश्चन कैटेगराइज हैं टॉपिक वाइज।
ओके सर।
ठीक है
सर, बिकॉज अगर लेक्चर्स हिंदी में रखें थोड़ा कम्युनिकेशन इजी रहता है।
हाँ, तो नेक्स्ट टाइम अगर सभी को हिंदी आती है, कोई ऐसा है जिसको हिंदी समझने में दिक्कत है, सो एक्चुअली मुझे उसके लिए रखना होता है। समटाइम देयर आर सम कैंडिडेट फ्रॉम साउथ इंडिया और अदर, सो दे गॉट सम प्रॉब्लम इन हिंदी। एवरीवन इज फाइन इन हिंदी?
यस सर।
ठीक है, तो जब हमें कोई भी टिपिकल चीज अंडरस्टैंड करनी है या कॉम्प्लेक्स, तो वी विल ट्राई टू अंडरस्टैंड दैट इन हिंदी, दैट्स फाइन। ठीक है, तो अभी ये रहने देते हैं। और इसको रिकॉर्डिंग चाहिए होगी तो मेरे को मेल कर देना, और अगर आपने मेल कल नोट नहीं किया तो एक बार फिर लिख देता हूँ मैं। ठीक है, इस पर आप मेल कर देना कि किस डेट का आपको चाहिए, मैं आपको उसी ईमेल आईडी को एक्सेस दे दूंगा जिससे आप मुझे मेल करेंगे। तो ट्राई टू गिव सेंड मी मेल थ्रू जीमेल, जिससे आप यूट्यूब एक्सेस करते हो। ठीक है, चलिए फिर, बाय बाय एवरीवन। राइट नाउ आप अभी अगर कहीं प्रैक्टिस कर रहे हैं तो करते रहिए, और जस्ट वेट फॉर फ्यू 5-6 क्लासेस, देन यू कैन स्टार्ट and try whatever coding platform you are using. So at least let us finish a binary tree section so that you can go and finish all binary tree and BST section.
So sir, we can practice those easy recursion questions from the list you will send, and then
Yeah,
अगर
yes,
कोई
sure,
प्रॉब्लम होगी तो डिस्कस
हाँ,
नेक्स्ट वीक।
इवन जो इजी सेक्शन है वो जो भी जिस भी डाटा स्ट्रक्चर से आप फेमिलियर हो वो स्टार्ट कर सकते हो। जैसे एरे और लिस्ट तो कर ही सकते हो, और लिंक लिस्ट के भी इजी क्वेश्चन मेरे ख्याल से लिंक लिस्ट बनाना डिलीट करना तो आता होगा इस तरह
यस
से।
सर।
तो वो इजी क्वेश्चन आप हर सेक्शन के ट्राई कर सकते हो। आप हीप के छोड़ देना, हीप हम बहुत अच्छे से डिटेल में करेंगे, हीप कैसे बनता है और कैसे उसके एक एक ऑपरेशन वर्क करते हैं। बाकी सारे सेक्शन आप इजी क्वेश्चन ट्राई कर सकते हो। ठीक है, चलिए फिर मैं भी एंड, हाँ आप कुछ पूछ रहे थे?
और उस मतलब उन क्वेश्चंस में डाउट हो या नहीं हो रहे हो
हाँ, तो जो भी डाउट होगा, तो अगर काफी डाउट है तो मेरे को मेल कर देना किसी क्वेश्चन में, हम नेक्स्ट क्लास में ट्राई टू कवर दैट क्वेश्चन। ठीक है, तो जो इस
क्वेश्चन कब शेयर करोगे आप?
क्वेश्चन में व्हाट्सएप ग्रुप बना के उसी पे शेयर कर दूंगा, आज ही कर दूंगा अभी 1-2 घंटे में।
ठीक है।
ठीक है, चलिए फिर, बाय एवरीवन।
Okay, sir. Thank you.
Okay. Bye bye.
Thank you, sir.